Hello? Yeah. Start. A very good morning, my dear colleagues, delegates from NRF Spoke Institutes, and my dear students. So, I heartily welcome all of you to this NRF pair thematic workshop in energy, which is scheduled for today, tomorrow, and day after tomorrow. The workshop brings together NRF pair IIT Hyderabad faculty along with the NRF Spoke Institute researchers and the students we have who are already in the campus and working in the area of energy to this engage in meaningful discussion in energy, emerging challenges in energy. The 3 days workshop is thoughtfully structured to cover key themes on renewables, clean energy and electrochemical energy storage, reflecting the pressing global need for sustainable and efficient energy solution. As all of you know that the world is transitioning towards the low carbon future, the role of interdisciplinary collaboration and knowledge exchange become increasingly significant. Correct? So it doesn't matter. So the workshop provides a vibrant platform for sharing fundamentals, recent advancements, fostering collaboration, which is very important, and writing joint proposals, exploring novel research directions in energy and energy science and technology. So each day of workshop is dedicated to a focus theme. So the first day will be on renewable energy technologies, which will be coordinated by Dr. Rupesh. So, he will take care. Also, in the evening, we have a lab-in session which will be scheduled in electrical engineering department. The day 2 will be will be on clean energy and sustainability, will be coordinated by Professor Sayak. And the day 3 will be on electrochemical energy storage, so will be coordinated by me and Dr. Narendra along with Professor Chandra. The workshop will, remember all the 3 days you have lab visits. You can explore the lab as much you can actually. So it's not limited to 1 hour. You want to spend little more time, you can always spend. And even at the end of workshop, if you have some doubts, I request you should meet the faculty and go and interact with them. So that's what I told. The workshop will inspire insightful discussion, encourage innovative thinking and strengthen the collective effort towards achieving energy security and environment sustainability. So let me extend our sincere thanks and gratitude to all the speakers who agreed to deliver a talk in this workshop, and the participants from various Spoke Institutes, the research students and the volunteers, Mr. Aslam, the NRF pair coordinator staff here, for their valuable contribution in making this event successful. So again, you have any difficulty, do not hesitate to reach me. So we have 3 volunteers sitting outside. You have any difficulty, please let us know. Will share the number and will be happy to come and support you anytime. So again, thank you and welcome again to IIT Hyderabad, and have a wonderful day ahead and a happy stay here. Thank you. Dr. Rupesh, you can speak. The coordinators can speak.
So, very warm welcome to IIT Hyderabad, Professor Martha ji. Thank you for opening this session. And in addition to this energy workshop, maybe a non-technical thing, you can roam around our campus. It's very beautiful campus, around 500 acre. Yeah, we have a lot of, lot of amenities. Please enjoy. Please do enjoy our campus. In this workshop, we have participants from different institutes with the different areas. So this content may go slightly, challenging to follow if it is not fitting in your domain. But please do not hesitate to, approach us and get clarification on the content. Yeah, so the first session is by Professor Niranjan from the Mechanical and Aerospace Engineering Department. He'll be speaking on a wind turbine related stuff. So I welcome him on a stage and start the session. So after his session, we'll have one more session by Professor Pradeep at the same place. He'll be speaking on a smart grid. He'll be joining somewhere around 11:30. He'll be speaking for 1 hour. Then we'll have a lunch break. And after lunch break, I request all of you to visit the Department of Electrical Engineering. So from our guest house, at walkable distance, we have one bus stop. From bus stop, you can catch a bus and the bus will drop you somewhere at UBD Circle, is it? Yeah, so it's a hostel circle. You can drop there, you can drop down there, and then it's just walkable distance to our department, electrical department. We can see from bus stop or banner and board or building. So we request you to come there in a e-seminar hall in the Department of Electrical Engineering after this lunch break. Yeah, and once again, welcome you all for this workshop on energy theme. Thank you. In between, if you have any comment or any remark, opening remark, we are fine to take. Oh, yeah, please, Sanjay. Yeah, thanks.
Hi, I am Dr. Sayak Banerjee from Mechanical and Aerospace Engineering, and I will be in charge of hosting the second day of the workshop on carbon neutral fuels. We have a good list of speakers which will be discussing both CFD of carbon neutral fuels, kinetics of carbon neutral fuels, as well as AI/ML techniques for used in alternative and modern energy technologies, as well as carbon capture and storage. So I welcome you all to the first day of workshop and hope all 3 days are very interactive and informative for you all. Thank you.
Hello everyone, welcome all of you to the energy workshop under this ANRF pair program. So day 3 we are going to cover electrochemical energy storage, starting from the fundamentals of electrochemistry, taking you to the battery technologies. The future is enabled by the battery technologies if you want to achieve the clean energy transition. So this is where that lot of emphasis is given not only on the technical stuff but also on the hands-on training. As mentioned by Professor Martha, so feel free, it's beyond the, like office hours. You are always, can get the hands-on and visit the labs. Students are available, volunteers are available. So make use of this opportunity. Networking is very, very important. Wish you all the best and have fun. Thank you.
Can I remove this?
Okay, am I audible? Okay, good morning everyone. Yeah. Okay, fine. So I'll try to finish in an hour, 15 minutes, hour, 20 minutes or so. Yeah. Okay, so good morning. Good to see all of you. And thanks for joining us here. I'm Niranjan Kaisas. I am in the Mechanical and Aerospace Engineering Department. And this is the title of my talk. I'm going to be talking about wind turbine and wind farm design. So I see a lot of you are sitting clustered together. You can maybe spread out so that you're all relaxed and yeah, and at any point, if you feel a bit drowsy, you feel a bit sleepy, please feel free to walk up. Please feel free to get up, stomp your feet, wave your hands, whatever you want, so that you drive away the sleep. If you want to go ahead and take a nap, that's fine too. Either way. Okay, so I've divided this into 3 parts, and before I start, can I just know what is the background? I met some of the faculty members just now, but the students, what sort of a background are you from? Chemistry? Physics? Okay, so you're doing BSc or MSc? PhD students. Okay, okay. Anybody from engineering, from an engineering background? Okay, okay, fine. So this is my this is the outline. I've divided my talk into 3 parts. First, we'll give an overview of wind energy, and we'll talk about how do you design one turbine, and then how do you go from one turbine to multiple turbines, which is a wind farm. So we'll step through this. Feel free to raise your hand and ask any question at any point if you have a doubt. So I want to start off with a few graphs. I hope this is still audible. Let's talk about how much resource is available to begin with. Okay, so what is plotted here is how many turbines are installed. And what's plotted is not the number of turbines, but the capacity, the installed capacity. And on this y-axis here, what is plotted is what you actually, if you install these many turbines, what is the energy that will actually be generated? Okay, so that's the plot here. So let's do a thought experiment. And so in this room, which is maybe a few hundred square feet, we have about 20 people right now. So instead of 20, if we were to push in 200 people here, what would happen? If we try to fit 200 people in this room, what would happen? It'll feel crowded, and everybody is generating some carbon dioxide. They have some body heat, so there won't be enough space. 200, there'll be enough space. Maybe you can. We won't physically touch each other, but we'll interact with each other in some way. It'll become very stuffy and all that. Now, if you pack 2,000 people in this room, we won't have space to even move your hand, which is what happens in a lot of public transport. My hometown is Mumbai, and that's the local train is something like that. In this room, you have I don't know, maybe 2,000 people. So something similar is happening here. Okay. So let's assume you take the surface of the earth, and you put a few number of turbines. Okay, those turbines won't feel the impact of each other. But now if you keep adding more and more turbines, they're going to interact with each other. One turbine is going to affect, the presence of one turbine is going to affect the operation of another turbine. Okay, so that's what you see here. As you increase the installed capacity, that means as you increase the number of turbines, initially the power that is generated keeps on increasing, but if the turbines did not interact with each other at all, you would have this line here. But what happens is the power starts saturating. Okay, so if you install turbines on all the land that is available, this is the curve that you get. If you install turbines on on the entire surface, land, sea, ocean, everything, this is the curve that you get. Okay, and so this is the wind turbines on land at a certain height, above the surface, and this is wind turbines everywhere throughout the entire planet. Okay, so first of all, we see two things. One is that it saturates, and we will talk about why this saturates. How does one turbine affect the presence of another or operation of another turbine? That's one thing. The second thing is, see what these limits are. Okay, so theoretically, if you devote the entire surface, land surface, to installing wind turbines, you have a capacity of 80 terawatts, right? And here you have 250 terawatts. And to give you some perspective, the total global energy consumption is about 2 terawatts. Okay, so this number is a few years old, and this may have increased a little bit, but not too much. So what this means is that practically wind is an unlimited resource. So there is a cap, but the cap is so large that compared to our requirement, that practically it is an unlimited resource. Okay, so that's one thing to remember about the wind resource. It is, for all practical purposes, it is as much as you want, you can extract from the wind. Okay, this is another map of the an energy map of the world. Okay, this also gives you a lot of information, so I'll try to unpack this a bit. What you have here is a scatter plot. Okay, you have population density of different countries on the x-axis, and you have the per capita energy consumption on the y-axis. Okay, and every country is a dot here. So for example, India is here, China is here, United States is here, Canada, Australia, Russia are here. Okay, so, and I mean, you'll see all the 200 countries are here. So what does this tell you? This tells you lots of things. So if a country is sparsely populated, it's going to be on the left side of this diagram. If it is densely populated, it is going to be on the right side. If it is developed, its per capita energy consumption is high, so it's going to be on the higher side. And if it is a developing country, then it's going to be on the lower side. Okay, because a lot of people still don't have basic electricity. They don't use things like refrigerators or air conditioners and so on. So they don't use a whole lot of electricity. So in this context, you can see what's happening. So India is to the right and lower corner of this graph. Sparse countries like Russia, Australia, Canada, these are all continental-sized countries. They are to the left and top, and they're also developed economies. Okay, China is somewhere in the middle, and so on. All right. So now let's think about there are these different lines here on this figure with a slope of -1. Okay, let's think about what these lines represent. So what do you think these lines represent here? These are different energy sources, and so this curve is in a log scale, right? So this is in a log scale. So if you what is written here essentially is log of per capita energy consumption. That means watt per number of people. Okay, that's on the left hand side, or that's on the y-axis here. This here is some function of log of population density. That means people per square kilometer or square meter, right? That's this figure here. And specifically, if you think about this particular line, which is a line with a slope of -1, what you have is this is a line with a slope of -1 is x plus y equal to constant, right? That's what a line with a slope of -1 is. So if you write that here, what you will see is this is log of or minus log of people per square kilometer plus some constant. All right. So this line, any line with a negative -1 slope, is this function here. Log of watts per people is equal to negative of log of people per meter square plus a constant. So if you rearrange this, you bring this to the left side, and so you now have log of A plus log of B, which we all know is log of A into B, right? So you get log of this multiplied by this, which is watt per meter square, is equal to constant, right? Which means what this line represents is a watt per meter square equal to constant sort of a relation. Okay, so these are different energy sources, and these are energy densities of different energy sources. Okay, so for example, energy crops has an energy density of 0.5 watt per meter square. Wind power has 2.5 watt per meter square. Solar has, which type of solar it is? It has either 10 or 20 or and so on. Okay, all our conventional forms of energy sources, they are all much further to the right here. They all have, so if you have a power plant, if you have a gas turbine power plant, that will have, it occupies very small area and generates thousands of kilowatts or megawatts of power. So it will be in the 1,000 watt per meter square sort of a range. Okay, so what does this mean? So let's say you take the wind power plot here, all right, and a country like South Korea or Japan lies very close to this line. Okay, what does that mean? What that means is, if you take the entire area of South Korea and install wind turbines everywhere over there, okay, then it will be enough to generate the it will be enough to power all the meet all the energy requirement of that country. Okay, if you have a country which lies to the left and bottom, then that means that that country has more energy, more land than it needs to power its entire requirement. Okay, so India lies somewhere here. So if you, hypothetically again, if you take all the land mass of India and install turbines everywhere, then it's going to be more than enough to meet India's energy requirement. Okay, now of course you can't devote every available piece of land to only install wind turbines and generate energy. So that's not the point. But the point is, wind. So I mean, this sort of a map tells you a lot. Okay, if you take any energy source, you try to improve its efficiency so that it goes further to the right and top. That will give you some. That's what you want. That's what you're after. Okay, so one take-home message from this is wind energy is diffuse. This is something that we've seen in abstract, but this is showing with data. Wind energy is a diffuse, and hence what you have is you have large wind farms. Okay, if wind resource is good in a certain region, you try to install as many turbines as you can, and you have to spread them out because wind is a diffuse source. Right? Okay, so now let's come to more specific numbers. This is an energy. This is the map of India with contours of energy, contours of wind resource available at a certain height, at 100 meters above the average sea level. And if you add up all these numbers, you will get a capacity of 300. You'll get a number of 300 gigawatts. So which means at 100 meters, if you install turbines everywhere in India, you'll get 300 gigawatts, which is quite a bit, which is a fair amount of energy that is available. Okay. So as of December 2025, the installed capacity in India is fairly good. It is 50 gigawatts. So we have lots of installations. Several installations go back to the 1990s. We over the last 10 or 15 years, we've added a lot also. Okay, and this is going to increase. This is the targets are by 2030, you'll reach somewhere to 75 or 80 gigawatts of wind power. So this number is going to increase quite a bit. But if you look at how much of it is actually utilized, so if you see something called the capacity factor, that is quite small, that is only about 20%. And if you see the penetration, that means how much of the electricity that we all consume, how much of that actually comes from wind, that is also quite small, that is only about 4.5%. Okay, and the interesting thing is, even in countries that are very, very rich in wind, for example, Denmark has a lot of wind penetration. Even in those countries, if you average over time and if you average over the European continent and so on, these numbers are not too much, are not significantly different from what they are here. Okay, so what all this points to is there are many aspects that we need to work on, but one of those aspects is we need to understand the fluid dynamics of wind farms so that you increase the efficiency of wind farms. Okay, I mean, there is economics, there is pricing, there is control, there is grid control, grid stability. There are these long-term, I mean, there are a whole bunch of things that have to go right. But fundamentally, for somebody like me or somebody who's an engineer or a physicist, it's important to study the fluid dynamics of wind farms also, so that we contribute a little bit to improving these two numbers. Okay. All right. So yeah. So you all would have seen this. These are different types of turbines. This is a horizontal axis turbine. So you have, this is your large tower. There are 3 blades. And why is it called a horizontal axis wind turbine? Because the axis of rotation is horizontal, right? So the blades rotate along an axis which is horizontal. Okay, the axis is straight up, vertical, and the blades rotate along this vertical axis. So this is a vertical axis wind turbine. And then there are many variants of these too. You have something called a multi-rotor wind turbine, where what you see is you have a tall column in between, and you have, instead of one 3-bladed rotor, you have multiple 3-bladed rotors on this arm here. Okay, there are many others. There is one, not one. There are multiple startups. One of them is based in Hyderabad, which also works on what are called corkscrew turbines. Okay, so there are lots of shapes, lots of designs that are out there. But this is what these are the 2 broad categories, and this primarily is the one that is used for utility scale power generation. Okay. Okay, so I've told you how the presence of multiple wind turbines affects each other. I want to make that a little more concrete. Okay, so let's think about what happens. We are getting a little bit into fluid dynamics. So if somebody has no idea of fluid dynamics, I hope this will still make a little bit of sense. So this is a wind turbine installed on the ground. You have your inflow coming in. This is the velocity profile. Right, the velocity is small close to the ground, and as you go away from the ground, it increases. As you go further up, the velocity, the wind speed increases. All right, and the wind turbine is extracting energy from this incoming wind. As a result, you have what is called a turbine wake. Okay, so the turbine wake is a region where you have reduced wind speed and you have increased shear and turbulence. So if the velocity profile of the inflow was like this, the velocity profile at a certain distance behind the turbine is going to be like this. Okay, so you have this deficit here. You have this hole in the velocity here, and that is because the turbine has extracted momentum or extracted energy from the incoming wind. All right. Any question? Anybody? Okay.
So what does the capacity factor mean, sir? In previous slide, it's only at 20%.
Yes.
What does it mean, sir?
So capacity factor is calculated for a power plant, and generally it is some measure of efficiency. How much of the capacity is actually being utilized? So
it's underutilized.
it is underutilized. Yes, 20% is really small. Yeah. Yeah. So you don't. So this is the picture with a single wind turbine, and as I said, you rarely have one single turbine. You have multiple turbines arranged close to each other. And what is going to happen is the wake of this turbine is going to affect this turbine. The wake of these 2 turbines together is going to affect this turbine, and so on. All right. So you have interactions between multiple wakes in a wind farm, and in general, those interactions will depend. I mean, the first thing that you can think of is if you want to reduce these interactions, what can you do? You can increase the spacing here. Right. As you change the spacing, if you place the turbines far apart, those interactions are going to go up or down, right? And in general, if you have a 2-dimensional area, you have not only do you have spacing along one direction, you also have spacing along the transverse direction, so Sx and Sy. So both of these in together, the horizontal layout will decide what sort of interactions are happening, right? So this is what you see in this very famous picture. Okay, so what you have, so this is a picture that was taken from a helicopter of an offshore wind farm. This is an actual picture, and you see a row of turbines here. You see another row of turbines behind that, and so on. Okay, and the wind is exactly directed along these columns. Okay, so you have these columns of turbines, and in this particular instant, the wind is exactly aligned along those columns. And as a result, what happens is that if you see the power generated by this line of turbines, that is a high number here. As you increase the turbine row, as you go further and further into the wind farm, you can see that the power drops quite a bit. Okay, and this drop, as you can see in this particular instant, is about 40%. So whatever was the power of the first turbine, the power of the second, third, and fourth turbines is only about 60% of the power of the first turbine here. Okay, so this is very, very large. This automatically brings down the efficiency, or if you've installed 10 turbines with a capacity of 2 megawatts each, you would expect to get 20 megawatts, but this will automatically ensure you get much, much less than that. Right, so this is the problem of, this is how the turbines interact with each other. This is called the problem of wind turbine wakes. So yeah, so power and wake losses are a strong function of the position of the turbine. All right, so now the wind is not going to be along one direction, the wind is going to change. So if you have a wind farm, if you have a certain arrangement, that the wind is not only going to come along one direction, but it's going to change in direction. Okay, so that is what is shown here. So this is one particular wind farm. So you have three turbines in this place, some 5 turbines here, and so on. You have this sort of a layout. And if you look at the power generated by this column of turbines, okay, normalized by the power generated by these front turbines, when the wind is generally coming from this direction. Okay, that's what is shown in this figure. So as the wind direction changes, so this direction is 225. Let's call this 225 degrees. Okay, so 0 degrees is top to bottom, 90 is from right to left, 180 is from bottom to top, and so on. So this is 225. All right, so 225 degrees, if this is the direction from which wind is coming, and if you allow the wind to change a little bit from this side and that side, so the x-axis here is going from 195 to 235. So at 225, where you have perfect alignment between the wind and the turbines, you see that there is a big drop. Okay, so the first row of turbines is always generating highest power, but as you go in and in, you see that row 2, row 3, row 4, and so on, they have a sharp drop around this direction of perfect alignment. Okay, by the time you reach, say, row 7, row 8, so that by the time you reach these rows here, it doesn't matter where the wind comes from. It is always generating very, very less power. Right? It is always generating only 40% of the power of the first row, because no matter where the wind comes from, some turbine is obstructing the wind. Okay, so that's what you see in this picture. So what I want to drive is power generation is dependent on the layout of the turbines. It is also dependent on the direction from which the wind is coming. Yeah. Correct. That's the question. So the question is, if row 7 and row 8, by the time you come here, the power generation is so small, why do you bother that? So that's one design parameter. How many turbines do you install? And do you only install them in 5 rows and then stop? It's an optimization problem, and that's a design parameter. So in this particular case, why was it designed? Why was it designed this way? Maybe there could have been a better design, right? Okay, and so that's the broad idea. And what you also need to realize is the wind itself changes quite a bit, whether it is summer or winter, whether it is monsoon season in India, whether it is a morning, noon, or night. Okay, so all of these factors are going to affect how much how much power a wind farm is going to generate. Okay, so this is a compilation of all the factors that we can think of that affect the generation of a wind farm. Maybe there are others, but this is what power generation depends on. Okay, first is what is your actual turbine. whether that turbine itself is designed correctly or not, how many blades do you have, how fast are they rotating, what sort of wake characteristics they have. Okay, then the second is how the wind flow is coming in. If the wind is 5 meters per second, you're going to generate a certain amount of power. If it is 15, you're going to generate another amount of power. Okay, so what's the turbulent inflow wind? Those are the two primary things. Then you also have things like stratification, density stratification, what happens on the inside the surface. Okay, so if you put turbines on land, the wake will be different. If you put turbines on sea, the wake will be different. If you put it on marshy land, the wake will be different. If you put them on hills, the wake will be different. So what is happening on the surface, by the ground surface, that also affects things quite a bit. Okay, and you also have things like Coriolis force. Okay, so we all know that the Earth is rotating, and if you install a wind farm in the southern part of our country, say Chennai, somewhere around Chennai, the Earth's rotation has a different effect there. If you put it somewhere in Ladakh, where also you have a lot of wind resource, that is going to have a different. The Coriolis forces there are going to be different. Okay, so that also affects how this wind farm is going to behave. And so this is a multi-length scale and multi-time scale problem, and that is what makes it challenging, as well as it makes it a lot of fun. Okay, so it's a challenge for numerical simulations because you have to resolve a large range of scales, and you have to run for a large enough time, and also extract meaningful information while doing so. Okay, so how do we go about designing a specific problem? So this is a fairly complicated problem, many aspects to it. So what you typically do is you can take this and break it down into some sub-problems. All right, so one thing is you can think of designing only the turbine. Okay, so you have different types of turbines. What is the best position in which you can operate them? What should be the cost, lifetime, what sort of maintenance it is needed, and so on. So all those considerations will drive how do you design this individual turbine. Okay, and then you have the wind farm design, where you need to decide how many turbines to install in a given piece of land. Exactly where do you place them? You need to think of grid frequency, maintaining the stability of the grid. You need to be able to think of being able to match supply and demand. So for wind power forecasting is very important under those situations. Okay, and so when you're talking about one turbine, the typical scale of a turbine is about 100 meters, right? The diameter, one turbine that you see is 100-meter diameter. That's the typical scale of turbines today. So now imagine what 100 meters looks like. 100 meters is, how much is one story? How much is one floor of a building? Any idea? 12 feet, 15 feet. So 15 feet is about 5 meters, right? So 100 meters is a 20-story tall building. So you have a 20-story, your blade is half that size. The size of the blade is like a 50-story building. So you have such a huge blade that is spinning. And that's what you have when you're talking about a turbine of a 100-meter scale. Okay, you may have seen a few on this highway, especially. You very often see trucks carrying these turbine blades, and those blades are also carried in sections. So you have one section that is at the root, and then you have a tip section. So yeah, these are massive things. Okay, so the last slide I have on the introductory part is this. So we've talked about wind turbine scale and wind farm scale. Okay, so this is ranging from about 100 meters to 1 kilometer and about 1 kilometer to 10 kilometers. So if you have, say, a 10 turbine wind farm or a 20 turbine wind farm, and the typical size of that wind farm is going to be about, say, tens of kilometers. Okay, in terms of how fast things change, that's the time scale. So on a turbine, the turbine blade rotates at about with a tip speed ratio of about 7 to 8, and that means that a flow structure that comes into a turbine passes through it in a few seconds or a few minutes. Okay, at a wind farm scale, it can be between a few minutes to, say, 10 minutes to 20 minutes, half an hour or so. All right, so these are the things that we will focus on in this session today. But there is also the airfoil scale. So if you think of designing one particular blade which is spinning, there you're talking about designing this airfoil. At every station of the blade, you have an airfoil. So designing this airfoil, which operates at smaller length and time scales, and then you think about an entire country, powering an entire country, where you have to think about what is the effect of one wind farm on another wind farm, which is say in the neighboring district, or say 2 districts from this one. Okay, so there you have to think about much larger scale phenomena, mesoscale and macro scale phenomena. That is, all of this is within the atmosphere. So these are atmospheric scales. These are much larger than wind turbine and farm scale. So I'm only going to talk about the second and the third for today. Okay, but what I want to tell you is that there is a scope for everything. So there is scope for making improvements, making tweaks here and there on each of these length and time scales. All right, so the summary of the first part is that we have an unlimited, practically unlimited, it's not actually unlimited, there is a cap, but for all practical purposes, it's an unlimited resource. But it's a diffuse resource, which means one turbine is not enough. You're going to have to install many, many turbines. Okay, a big challenge with this is wake losses. And this is a multi-scale problem. So it is both challenging and a lot of fun. Okay, any questions so far?
So what are the environmental factors or is the wind farm affecting environment?
Right, that's
Is it truly a green energy or is it doing something else?
right. So yeah, I'll ask an extreme version of your question. The extreme version of your question is, if I install a lot of turbines, will the wind stop blowing?
No, not
That's the extreme question, right?
people are affected, the birds
Correct.
are affected.
Correct. Yes.
Is it affecting the nature?
Correct. Yes. So it does affect nature, and there are contradictory studies. One study says that if you install a turbine here, if you install a wind farm here, it leads to a decrease in rainfall. A few studies say that if you install a turbine wind farm in this case, it leads to increase in precipitation. So I think it is very location specific, but it definitely has an impact. It definitely has an environmental impact. About birds or bats, that is a bit more clearer, that the harmful effects are quite limited, because these blade turbines rotate fairly slowly, and they have a very significant acoustic structure, acoustic signature. So birds and bats can hear, or birds can see, but bats hear. And even bats know that there is something spinning here, I should steer away from here, so they can go around from there. So the politicians will say different things, but the people who are pro something will not acknowledge any harmful effects. People who are against will say that nothing good can come from here. But I mean, what I would say is impact on birds and bats is less, but impact on general environment, micrometeorology is quite a bit, is not insignificant. And we need to account for that. We need to be sure that if you put a turbine in a certain region, you don't end up harming other economic activity, say farming or something like that in that region. Yeah, you had a question.
Sir, earlier you have said about 3 types of turbines. So is it area dependent that which turbine should be suitable to which region, which be more effective to certain area? Is it certain thing like that?
Yes, definitely. So yeah, I said these 3 types of turbines. These are the largest turbines that you have. I mean, these will scale, the horizontal axis wind turbines, you can build them, if you build them bigger, you will get more efficiency here. With vertical axis wind turbines, there are other considerations. So these are typically 1 order of magnitude smaller than these. So if the typical size of these is 100 meters, the typical size of these is 10 meters. So you have maybe, so this one generates megawatts of power, this one generates a few kilowatts or a few hundred kilowatts of power.
Residential purpose they can be erected.
For residential purposes, these can be used, yes. And there are multiple attempts to do that. So the way you have decentralized solar generation, decentralized wind is also, people are trying that. It has its limitations, but if you want to do that, this is a better choice than this one. So yeah, so I mean, the region definitely does matter, yeah.
I have one other
Uh, there are hard to say one reason. Uh, so one thing is some of this is not very well understood, and what people have done is you have an area, you have a certain budget. Let me put all the if I have the money to install 10 turbines, let me install 10 turbines here. Okay, but we saw that doesn't work. So some of it is a design problem. But a lot of it is also that oil is subsidized in different ways. The same subsidies are not given to renewable sources. One big problem with wind or all renewables is intermittency. That means the wind will blow now, and after 10 minutes it will stop. And then after half an hour it will ramp up again. Okay, so this intermittency is a big problem. And when you want to supply electricity to the grid, intermittency causes problems. And so if a grid operator is trying to match demand, that person would always prefer a source that is stable rather than something that is going up and down. So that integration of renewables with the grid, that is a big problem, and that contributes to a lot of this resource going unutilized. Okay, so that's where batteries become very important. If you can use this intermittent resource and store the energy using batteries or something, and then utilize it through the battery you supply to the grid. That is one way in which you can improve the utilization of wind. Okay, so I would say two things. One is you don't understand wind energy systems so well, and second is integration with the grid. That is a big problem. But I mean there are other reasons also. Okay, yeah.
Climatic conditions already going to affect.
Sorry.
Climatic conditions. What is the effect on the power generation?
Yeah, a wind farm affects the local climate. It won't affect. It will affect the local micrometeorology. So we will have maybe small changes in the weather around that wind farm, but on the climate scale it won't matter. On a climate scale it will be beneficial. So if we take our energy sources and convert a significant fraction of that to wind, for example, let's say 10% of our energy, 20% of our energy starts coming from the wind, then on say 20 years down the line, 50 years down the line, it is definitely going to be beneficial, because we will not be generating that much carbon dioxide, that much methane, so the temperature won't rise that much. But in the vicinity of that wind farm, there will be some positive consequences, some negative consequences. Like you have a coal plant, people living around that coal plant suffer terrible problems. So we won't suffer that bad problems with a wind farm, but there will be some problems. Yes. Noise is a big issue. Yes. Yeah.
In Anantapur, we have a lot of windmills. They are all located in hills.
Yes.
Earlier, those hills were actually nobody goes to the hills also.
Right.
Those places they are erecting their windmills.
Right.
You know, a lot of windmills around.
Yeah. Anantapur, so Telangana as a whole doesn't have such a good resource, but Anantapur district is the second windiest district in India, according to some estimates.
We come out of Anantapur, we see a lot of windmills.
Yeah. So that's another problem. If you have a state which is overall, when you average over the entire all the districts of that state, you don't have such a good wind resource, then that state government has no incentive to promote wind. But you might have certain pockets within that which should be tapped, which should be utilized. So in all these these are all regulatory issues or administrative issues, which all prevent wind from. I mean, any resource has to have the correct policy framework in place.
Are the returns good for the investors, sir? Those who invest in these farms?
It looks like it because a lot of people are investing. So these 50 gigawatt is all private. Mostly it is. I mean, I think 99% of it is private. A few of them may be research institutes or some government demonstration projects, but all of these are private players. So there has to be. They should be seeing something, which is why they're investing. Okay. All right. Okay. So let's carry on. Let's talk about the second part now, which is wind turbine design. And we'll go a little faster. So we've seen this. These are the different types of wind turbines. horizontal axis, vertical axis, and then some combination of these. Okay, so let's think about how do you design a horizontal axis wind turbine. Okay, so to be able to design, first thing is you need to be able to predict, right? If I want to warm up, say, a cup of tea, I want to make a cup of tea. First thing is I need to be able to predict if I take this much amount of water and put it on the gas and turn the gas to a certain height, or I mean, in today's context, if I put it on a hot plate, not an LPG gas, if I put it there and I keep it for 2 minutes, will the water start boiling or not? Okay, so if I can predict that, then I can adjust my how much water should I take, how much should I heat it up, and so on. So if you can do the forward problem, that is predict, given certain design choices, predict how the wind turbine is going to behave, then I can do design. Then I can say this is the performance that I want, and these are all the levers that I have. I can change the diameter, I can increase the rotation speed, I can change the blade shape, and so on. Okay, so the question is, given the turbine height, turbine dimensions, blade properties, rotation speed, and so on, can I answer questions about the aerodynamics, and can I answer questions about the structural loads? Okay, so for example, when it comes to aerodynamics, what is the lift and drag characteristics of the blade? What for the entire rotor, what will be the thrust coefficient and the power coefficient? So I'll define what thrust and power coefficient are in a bit. Again, the second thing is what will be the structural loads on the blade. You don't want the blade has to be flexible, but it should not be so flexible that it snaps, right? So this is again an exaggeration. This is also an exaggeration. The blades do bend this way and this way, but they don't bend this much. But this is just shown for illustration. Okay, so those are the two primary questions. Given certain assumptions about what the turbine is, blade is, how fast it is rotating, and so on, can I predict the aerodynamics, and can I predict the structural load? If I can do that, then I can do the reverse problem, which is design. All right, so how do you do the forward? How do you solve the forward problem? This is where we come to a little bit of computational fluid dynamics. So how many of you have heard of CFD? Several people have. How about the students? A few people have. People with chemistry may not have. People with physics background would probably have heard of this. So this is essentially, so what you have is you have fluid flow is governed by these equations, which are called Navier-Stokes equations. And this is what those equations look like. Okay, so you have essentially three equations. One is continuity equation. This is the momentum equation, and this is equation for energy written in terms of temperature. Okay, so these are coupled three-dimensional partial differential equations. All right, so these are also nonlinear because you have a u, which is your velocity, along with another u here. So this is a nonlinear term here. Okay. Then these are coupled because you have temperature, which affects density. As you all know, if air is heated up, any fluid, if it is warmer, it becomes less dense. If it is cold, it becomes more dense. So density is a function of temperature. That temperature has to be solved for using this equation. Okay, so here you have an equation for U, which involves temperature. Here you have an equation for T, which involves U also. So these are all coupled to each other. Okay, so these are Navier-Stokes equations. These are fairly difficult to solve for any general problem, right? So what you do is you take these equations, you discretize, you take your domain. Let's say I want to predict the flow around a blade or a turbine rotor. You need to discretize these equations on structured or unstructured grids. Okay, and then you have to solve them numerically. So what that means is you will be able to finally, after you solve them, you will be able to tell what is the three components of velocity, that is UVW. You will be able to predict what is the pressure. The pressure is one part of the Navier-Stokes equations here. And what is the temperature at every point in your domain. Okay, and to be able to solve this, you have to write code. Then that code cannot run on one processor, it has to run on multiple processors. Okay, so you have to use a combination of CPUs and increasingly GPUs. And so you need to use these massive supercomputers to solve these equations, which will give you useful information about the flow field around whatever system it is that you are simulating. Okay. All right. So let me take the example of simulation around a blade. All right. So if you want to simulate the flow over some blade, what you need to do is you need to discretize the domain around that blade in this manner. Right, and very often you need very fine resolution around the blade. So you have the blade here, which you can barely see, and you have a very fine collection of grid points around that. Then you have a collection of slightly coarser points here, and then in the far away region from the blade, you have further coarsening of the mesh. Okay, so this is an illustration of the mesh, and you need to you take this, you discretize those equations on the grid like this, and you solve for the unknowns at the centroid of every mesh point here that you see. Okay, so why do you need these very fine meshes close to the blade and so on? Because you want to resolve what is called separation on the blade surface. Okay, so these are all fluid dynamical terms, so I'll skip over that. But what do you get from all that? You get what are called CL, CD, and CP curves. That means you get the lift coefficient, drag coefficient, and pressure coefficient curves. This is one example. Okay, so this is the pressure coefficient as a function of the position along the chord. So I have my blade, which is rotating like this, and if I take one particular cross section here, and if I look at that airfoil shape, I look at the chord. Okay, on the upper surface of that airfoil, this is the pressure distribution. On the lower surface, this is the pressure distribution. And because of because of the difference between these two, I get some contribution to the lift. Okay, so this is what is a significant component of the lift that is generated on that airfoil, and that is what causes the blade to rotate. Okay, and here what you see is a comparison between three different methods. One is two of them are CFD. One is, I think, an experiment. Right. So if you do an experimental and a simulation campaign like this, what you need to do is you need to validate your CFD results with experiments. Okay, because CFD is not perfect. No method is perfect. If you conduct experiments, that will come with its own experimental errors, its own limitations, and so on. And if you do a CFD, it will have its own limitations, grid dependence, and so on. So it's always important to do this validation exercise where you see if you can get the same answer from two or more different tools. Okay, so that's if you want to do a CFD, this is what you do. You discretize your domain, you solve those equations, and then you validate whether you are getting the correct answer for something that you already have reference results. Okay, now the design can also be done using simpler tools. Right, so you can use what is called, there are a whole host of simpler theoretical tools. One of them is a combination of what is called the 1D momentum theory and airfoil analysis. If you combine these two, you get what is called the blade element momentum theory. Okay, so this is the blade element momentum theory, which is quite useful for doing designing a rotor. So I'll briefly talk about the 1D momentum theory part. We won't talk about the full BEM part. Okay, so what happens? So let's think about what happens when you have a blade, when you have a turbine, and you have wind coming in. All right, we all know that acts as an obstacle to the wind, and it's going to extract energy from the wind. Right. So if I think about a disk that is completely impenetrable. Okay, so if I think of a non-porous disk, if I think of a rigid disk and wind is coming in, what will happen? What happens in that case? What will the airfoil, what will the flow patterns look like? So let's say I have flow coming in like this, all right, and I put a rigid disk here, all right. So this disk is rigid; it cannot allow anything to pass through it. Okay, this is an impenetrable disk. What happens? What will the flow streamlines look like? So you'll have some streamlines that go up like this, some that come down like this, okay? And so flow will go around.
Check. Check, 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 check. Check, check, check.
It turns out that that's the most of the vehicles I see only 3 blades. Yes, correct. So you can derive that. So this blade element momentum theory allows you to figure out as you increase the number of blades, what is it that you gain and what is it that you lose. It turns out that 3 is an optimal for these moderately sized large sized wind turbines. If you see the smaller sized wind turbines, they have larger number of blades typically. Okay, so if you have a porous disk now, so what happens is the velocity here is say v0, and as you go here, the velocity here is not 0, it is some number u, and as you go further out, as you go further downstream, the velocity will become something, let's call it u1, all right? If this were a porous, if this were not a porous disk, the velocity here would have been 0. All right, but because this is a porous disk, the velocity, average velocity along this rotor area is u. All right, so that's what is written here. That's what is shown here. What you see here is you have an inflow v0, and you have a velocity u here, and you have a velocity u1 at the far downstream of this rotor. And if you look at the plot of velocity as a function of x, this is what it looks like. This is v0, then it drops to u, then continues to drop and comes down to u1 at very far downstream. Okay, the pressure looks like this. The pressure is some P0 upstream, and just around the rotor, the pressure increases, rapidly decreases, and then it recovers again after that. Okay, so only around the disk, only along the rotor, you have this large pressure jump, but very far upstream, very far downstream, the pressure is the same. All right. Okay, so what we've done is we've seen that if you assume the rotor to be a porous disk, which is a good assumption, you can see what the velocities are going to be. They're going to be v0, which is greater than u, which is going to be greater than u1. And using these, you can define what is called an induction factor. Okay, so induction factor A is something that relates the velocity at the disk to the velocity upstream. So induction factor A is defined in this manner, u is equal to v0 into 1 minus a. And using this, you can then derive what will the velocity be at far downstream, u1. It turns out that this u1 will be v0 into 1 minus 2 times a. Right? So this is an assumption. This is what follows from this assumption. Or this is a definition of the induction factor A, and then the second equation here follows from that definition of induction factor. All right? Okay, then what you can do is you can now find what the thrust force is going to be. Okay, so what's the thrust force? You all know from 12th standard physics, what is the definition of force? What is the definition of force? Force is mass into acceleration. Okay, in general, so in general, it is rate of change of momentum. right? It is rate of change of momentum, m into v, and d by dt of that, right? Very often our mass is constant, that's why this becomes m into acceleration. Okay, but in this case, what we have is, if you draw one control volume around this this rotor, what you have is the mass flow rate is changing, or you have a constant mass flow rate. Mass is constantly coming in and going out of this control volume. All right. So in this case, what it boils down to is m dot, that is the mass flow rate, multiplied by a difference in the velocities. Difference in the velocity far upstream and far downstream. That is v0 minus u1. Okay. So force or thrust is, so that's what is written here. Okay. Thrust is mass flow rate. The first term here is mass flow rate, and then you have the difference between velocities far upstream and downstream. All right. Okay, so this is just the definition of thrust, and now you can plug in what is the value of u in terms of v naught. So you get a v naught into 1 minus a, and you can plug in what is u1 in terms of v naught. So you get v naught, one more v naught, which becomes a v naught square, and you get a 1 minus 2a here, and that finally gives you this formula for thrust. Okay, so the thrust is given as a function of the inflow velocity v0, undisturbed far upstream velocity v0, and the induction factor here. Right? Now from this you can, because you want to compare across different turbines, one turbine which is say 5 meter diameter, another turbine which is say 50 meter diameter, because you want to compare across turbines, you normalize this. Right? So you compute what is the thrust coefficient, which is Ct, which is thrust divided by half rho a v0 square. So this normalization by a, that takes care of whether you have a small turbine or a large turbine. You will get the same thrust coefficient if the turbine is the same otherwise. Similarly, if the inflow is 5 meters per second versus 8 versus 10 or whatever, to take care of that, you also normalize by v0 square. Okay, so that gives you the formula for thrust coefficient. Ct finally becomes 4a into 1 minus a. All right, so what we've done is, if you assume some induction factor, you now have the formula for the thrust coefficient in terms of that induction factor. Okay, similarly, we can talk about power. How much is the power that is extracted by this turbine? So power, as we all know, is force into displacement. Force into displacement is work, and rate of work is power, right? So force into velocity is going to be your power, right? So power is T into U. And again, if you do that same algebra, you will see some product of A and 1 minus A and so on, and a V naught cube here, all right? And from that, you can determine what is the power coefficient. And the power coefficient is Cp, which is the actual power divided by half rho a v naught cube. And so now you get this formula, which is 4a 1 minus a the whole square. All right, so what we've done is, using, so this is all 1D momentum theory. We've calculated a formula for the thrust coefficient. We've calculated a formula for the power coefficient. And it turns out that this is a nice parabola. This is a quadratic equation, right? This is a parabola. This also is a cubic equation. Okay, this is cubic in A. So this is going to have a peak. This is also going to have a peak. So can I quickly ask you to calculate where the peak will be for this one and this one? So how do you do that? You just differentiate with respect to A and set that to 0 and solve for A. So this will be for 1 by 2. Okay, and this one will turn out to be for 1 by 3. Okay, you can do that and check that this one will peak at 1 by 2, this one will peak at 1 by 3. And now if you actually plot, you simply plot this Ct as a function of A and Cp as a function of A, this is what you get. Okay, this is the line for the thrust coefficient. This is the line for the power coefficient. Okay, because A and 1 minus A, they are symmetric, but as A goes from 0 to 1, you see that this peak is symmetric, this curve is symmetric around 0.5, and that is where it peaks. This one is shifted to the left. Okay, the Cp curve is shifted to the left. And this tells you this very interesting observation that power is going to be maximized at a certain value of 1 by 3, and the maximum power is close to 59%. Okay, this is called the Bed's limit. All right, so this is a very famous result. This tells you that if you have certain power, if you have certain energy blowing through the wind, no matter what sort of obstacle you put there, the maximum power that you can generate is 59%, 59.3% of that power that is blowing through the wind. Okay. Now it turns out that actual wind turbines today, they can achieve up to 45-50% of that. So if 59% is the absolute maximum, a standalone wind turbine is good enough to achieve 80% efficiency with respect to that number. So with respect to the energy that is blowing, it is able to extract about 50% of that, maybe even 51, 52% of that energy. Okay. That affects the capacity factor. Yes, that will affect the capacity factor. Yeah.
So what is A, sir?
A is called the induction factor. Yeah, A is the induction factor here.
The ratio?
A is the ratio of the velocity at the disk. A is, yeah, this is the definition of A. 1 minus A is the velocity at the disk divided by velocity upstream. Okay, so this is the definition of A. All right. So, so what we've seen is thrust and power are coefficients of the induction, are functions of the induction factor. Now the next question in the design process is how do you get that induction factor, right? So if I have a certain rotor, that is going to imply a certain induction factor, and that induction factor is then going to determine how much thrust and power I'm generating. So the next question is how do I get that induction factor? What is it dependent on? And that is where the second part of this, that is the airfoil analysis, comes in. Okay, so if you include effects of rotation, you introduce another rotational induction factor. Okay, we had talked about axial velocity and axial induction factor. Similarly, you can have a rotational induction factor, which is typically termed B. And now what you can do is you can figure out, I mean, using simple analysis like what I showed you, you can write equations for A and B as functions of the number of blades, how fast they are rotating, what is the blade twist chord, and what airfoil shapes make up that actual blade. Okay, so that all that together is called the blade element momentum theory, which is not very difficult. I mean, it's taught regularly in undergrad classes, but that is a very, very useful theory which can allow you to relate the tangential and axial induction factors as a function of actual geometry of the rotor. Okay, so BEMT, blade element momentum theory, is the first complete theory that allows you to make a first design of a wind farm, of a wind turbine rotor. Okay. Where does CFD come in now? Full 3D simulation, full CFD simulation helps you relax certain assumptions that are made in the blade element momentum theory. Okay, so for example, one assumption is that you have inviscid flow, viscosity is not important. Another is you have no separation along the blades of the turbines. Okay, so the consequence of inviscid flow is that you have these sharp corners here. Okay, in a viscous flow, this is not allowed. In a viscous flow, you cannot have a velocity being something here and a velocity being very large right next to it. Okay, so this sharp jump that you see here in the velocity profile, that is not allowed in practical, in actuality. But in an inviscid theory, if you do that, this thing is allowed. Okay, and so this is a problem, or when you incorporate effects of viscosity, this thing will go away, and you will get better representation of the actual flow field. Similarly, the pressure doesn't recover exactly to the previous extent, again because of viscous effects. So if you do a full CFD, you will not incorporate mistakes like this. All right, and because of this, you can get corrections of about 10%, 12%, and so on. Okay. So you do a first design using inviscid blade element momentum theory, and then you can do corrections on that to the tune of 10% or so to get a much more accurate design. All right. So so this is, for example, what the flow will look like. If you have a uniform inflow, if you have a sheared inflow, this is what it will look like. You have 3 turbine bladed rotor here, 3 bladed turbine rotor here, and same thing here, and that's generating what are called these tip vortices, okay, and those are seen here. So anyway, so what you see here is a comparison between different design tools. One is a full CFD simulation that is given by this what is called ALM. And then you have blade element momentum as one of these design tools here. You can see that there is a reasonable agreement, but you have, for example, between ALM here and ALM here, there is a small discrepancy here. Okay, so the blade element momentum theory gets the overall picture correct, but these small, tiny, seemingly tiny deviations on this plot are what are very, very important. When you're doing a design, you cannot do a design if you have this level of deviation between the actuality and what you're assuming, and that can make or break a turbine. Okay, so everything is important. You do a first design using simple models, and then you do a CFD, and then refine your design according to that. All right. Okay, so that's the second part of my talk. So wind turbine design can be done based on theories such as 1D momentum theory or blade element momentum theory. And you can then use a full 3D CFD simulation to refine your design. All right. Any questions?
Sir, what factors affect this mass flow rate?
So mass flow rate is simply product of density and volume, right? So mass flow rate is just density, area, and velocity, right? So rho AX would have been volume, and rho AX would have been the mass. Instead of x, you have dx by dt, that is velocity.
It only depends upon the velocity of the wind.
Yeah, and the dimension, and how big the rotor is, area. And it also depends on the density, of course. Yeah.
So density of A or density of
Density of the air. Density of the air. Yeah.
density of air and the dimensions of the turbine are fixed.
Yes.
Then it simply depends
It simply depends on the velocity. Yes, correct. Yeah, but this velocity u is dependent on the v naught, the incoming velocity through this induction factor A. Okay. So if you have a large induction factor, then this velocity is smaller. If you have a smaller induction factor, this velocity is larger. So you have either a higher mass flow rate or lower mass flow rate according to that. Okay.
Sir, role of humidity is not considered in design of the turbine.
In the preliminary, it is not, but in a CFD, you can include those effects if you want. Yeah. So when it comes to offshore wind farms, that becomes quite crucial because you have a lot of salinity in the water, and you have a lot of moisture in the air. So
In offshore means on the sea, sir.
on the sea, yes,
What
yes.
about the coast, sir? Coast
Yeah,
also the same
there
thing?
also, yes, correct, yes, yes. So moisture can have a significant impact on the density of the air itself. So yeah, a moist air is generally very, very, very significantly different in density than dry air. Yeah. Okay, so let me go through the last part quickly. So now we are talking about wind farms now. Now we're talking about multiple wind turbines, one after the other. And this is a variant of the picture that I showed you in the beginning. You have the incoming boundary layer, and you have the boundary layer height here. And because of these turbines, you have an internal boundary layer that develops. And so power generation, fatigue loads, noise generation, environmental impact, these are the kind of questions that you're asking here. You're assuming that one turbine is given to me, or the turbine model is given to me. Now, how do I place these turbines optimally so that I maximize power generation, minimize noise, minimize environmental impact, and so on. Okay. So typically, when you talk about wind farms, this is the first row. So let's say your wind is coming from a certain direction. This is the first row. Then you have a cluster of wind turbine rows here. And so if you have a wind farm that is, say, 8, 10 rows, then you call it a cluster or a finite-sized wind farm. But if you have a wind farm that is 30 rows, 40 rows, 50 rows, 100 rows, and so on, then you call it a fully developed wind farm. Why is that? Because the internal boundary layer that forms because of these wind turbines then starts approaching the height of the actual atmospheric boundary layer. Okay, the actual atmospheric boundary layer is about between 1 to 3 kilometers. And if the effect of these turbines propagates all the way to the top of the boundary layer, then you have what is called the fully developed boundary layer. So generally what we say is up to the first, say, 10 rows or so, it is a cluster. And then beyond that, if your wind farm is so large, it is going to affect the entire structure, the entire boundary layer from top to bottom. Then we call it a fully developed wind farm. Okay. How do you solve, how do you perform CFD of this? You have to make many simplifying assumptions now. Okay, first is that you cannot resolve all the things that are happening very close to the blade. So I showed you how you can do a simulation where the blade is resolved by putting very fine grid points around the blade. That is not practical here, because if you start resolving every solid surface, and if you want to simulate a 100 turbine wind farm, that is, the mesh count will become very large. Okay, so instead of that, what you typically do is you introduce body force along the blade, along the line of the blade. And so this is done using something called the actuator line model. Okay, so there is one specific way in which you can treat how do you incorporate the effects of this in a full CFD simulation. The second thing is the ground effects of the ground are not, you cannot resolve those very clearly or very easily, so you introduce what is called a wall model. So these two changes have to be made to a CFD code, or these two simplifying assumptions have to be made so that CFD of a wind farm becomes practical. Okay. Okay, so I'll show you a few animations of a few simulations that I've done. This is what is called the Lillgrund wind farm. We are looking at it from the top. Okay, you have these dots. These are all individual turbines. The flow is coming from this 225-degree angle. Okay, and you can see that the flow. So these are instantaneous contours of instantaneous velocity. And as time progresses, you can see that there is a wake that is formed. The wake sort of meanders and so on. Okay, this is the same simulation, but two different cuts. One is a horizontal cut, and one is a vertical cut. And here you can see how the boundary layer or the wake develops behind these turbines here. Okay. So these were 48 wind turbines, 108 meter diameter, and the power rating of each turbine was 2.3 megawatts. Okay. Here is another simulation. So again, we're looking at it from the top. These are 30 turbines, maybe a bit hard to see. You see these vertical white colored lines here. Those are individual turbines. You have flow coming from the left. And you can see this is a very rich structure. There is a lot of scales embedded in this simulation. If you take statistics of this, you do time averaging, and you look at profiles. For example, 1, 2, 3 diameters behind this turbine. So this is row 4. So this is 1, 2, 3, 4. This is the 4th turbine. If I take different lines, and if I take vertical profiles along those lines, this is what I get. Okay, and those blue symbols are our results, and the open circles are from some previous simulation. And we see that there is a good agreement in terms of the mean velocity. Okay. Similarly, if I go back to the previous wind farm that we simulated, and again we look at the power as a function of rho, this is what you see. So the turbine number 23 is the first turbine in one of these columns here, and 16 is the last turbine here. And what you can see is the first turbine generates large power, the second turbine generates much less power, and so on. And again, what we are doing here is we are comparing our simulations with experiments, previous observations, and we see that there is a good agreement here. So I'm showing you that power degrades because of wake losses, as we see here. This drop here is because of wake losses. Okay, and we also see good agreement between simulations and experiments. This is what I was alluding to earlier, that validation is very important.
Why is there a spike at 27 cents?
Yeah, good question. So you see there is a hole here. So this layout is such that at one place there is no turbine. So this picture is along either this line or this line, one of these lines. So how many turbines do we have? 1, 2, 3, 4, 5, 6, 7. So it's probably along this line. So we have 3 turbines here and 4 turbines here. So this is along this line of turbines, and there is a hole here. And as a result, there is a larger spacing that is allowed here. So this turbine generates more power than the others. Okay. Okay, so what I've shown you is CFD studies can be done, but they are very, very expensive. So for example, this simulation took 65 million grade points, and it took about 60 seconds per time step on 384 CPU cores. And if I simulate for a sufficiently long amount of time, that would require me to simulate for 25,000 time steps. And all of this implies that so this entire simulation took about 17 days on 384 cores. Okay, and so we spent about, I think, close to 90,000 or a little more than 90,000 rupees for one simulation just on computer time. Okay, so from this we can get one result. So from this I can say that this wind turbine with this wind farm is going to generate this much power. All right, so of course this is not practical. We cannot invest this much amount of effort for one result. All right, so because CFD studies are expensive, the real practical purpose or utility of CFD is to help develop simplified models. Okay, and you cannot do a design to do a design. You have to do parameter sweeps, right? For example, if I say that I want to put 30 turbines versus I want to put 29 turbines versus I want to put 31 turbines, I want to sweep over a certain range of how many number of turbines should I put. Similarly, I want to sweep over what is the induction factor or what is the rate of rotation of each turbine blade. I have several candidates. I want to sweep over all those candidates. So those sort of parameter sweeps that are essential for design studies, they cannot be done using a CFD. Right? So what is feasible is you do a few parameter sweeps, but primarily you develop simplified analytical models, and analytical models is what you use for design. All right, so I'll quickly, for a couple of minutes or so, I'll talk about how these wake models are what these wake models are. So again, this is our schematic, which you're familiar with by now. This is a turbine, this is a turbulent inflow, and because of that, you have a hole in the velocity that is called the velocity deficit. Okay, so the velocity deficit simply is the difference between the velocity upstream, that is u infinity, minus velocity in the wake, that is u wake. So if you just take this difference, you'll get a velocity deficit. It will look like this. All right, and it is typically modeled. The velocity deficit is modeled in this manner. Okay, so the velocity deficit normalized by the upstream velocity u infinity is a function of x, y, z, right? It's a function of all three spatial coordinates. So this can be modeled as a c of x, a center line value, times some function which depends on the width of the wake, right? So the velocity deficit has a center line value at this point, and it has a certain characteristic width here, sigma, that goes into the formula for the velocity deficit, right? And so what you do is you assume a certain functional form for this f, and from that you can determine, from momentum conservation, you can determine what this c should be. R is the radial distance. R here is the radial distance. So I mean, for example, if I want to know what is the velocity deficit at this point, this R is my radial distance. Okay, and I mean, this is in one x plane you will have R. So R is a function of y and z, or both of them. All right, and we've developed a few simplified wake models like this, and this is what the centerline velocity profile, centerline deficit evolution looks like. This is what the velocity deficit looks like at one particular x. So this is at x by d equal to 6. This is at x by d equal to 8. So what is marked using those blue circles here are actual CFD results. And you have two different models, a Gaussian model and a top hat model. And the Gaussian model seems to work better. The top hat model gets the correct momentum balance and the correct energy balance, but the exact shape is not correct. Okay. So now if you have multiple turbines, so I told you about one turbine. Now if you have multiple turbines, what is the cumulative effect of many turbines? How does this wake? Because if I want to know the velocity deficit at this point, it is going to be affected by the wake of this turbine plus the wake of this turbine. So how do I combine these two? That is called wake merging. All right, and one way of merging wakes, these are all empirical, is that you take the delta U total as some empirical formula of this sort. So you take the velocity deficit because of one turbine, raise it to the power P, plus the velocity deficit of the second turbine, raise it to the power P, and so on, add all these up, and then take the pth square root, pth root of that sum. All right, so if P is equal to 1, this is called linear merging. If the P is equal to 2, this is called quadratic merging, and so on. So these are empirical, but there are more physics-based formulas that have been derived for wake merging. All right. Okay, so this is what the results look like. For example, if you have, this is the velocity deficit for a 5-turbine wind farm. First turbine is at 0, second is at 5, 4, 8, 12, and so on. Okay, and what you see is if you use Gaussian wake merging or Gaussian wake model with P equal to 2, you get sort of correct behavior, but you get the best behavior with top hat profile and P equal to 2. With Gaussian model and P equal to 1, that is linear wake merging, you get completely wrong results here. Okay, so similarly, so this is the velocity deficit, so this is the power. Again, you can see that LES is this black line here, and some models get it correct, some models don't get it correct, and so on. All right, and so these kind of models, they can be used for design purposes. Use of CFD is not practical. All right, so I'll end with this a short demo of this wind farm suite that we've developed. Okay, so we've developed some of these wake models, and we've put them on GitHub. So you can, so this is an example shown for a 5x4 wind farm. You have 5 turbines in this way, 4 turbines in this way, so you have 20 turbines here. And this is what the velocity, average velocity field will look like if the flow is coming from 270 degrees. Okay, if the flow changes from 225, then it's like the wind farm has rotated. And this is what the velocity profile will look like. This is what the profile will look like if the wind farm rotates the other way or the wind rotates that way. So 315. Okay, and I mean you can play around with this, and you can determine what is the power generated by every turbine under all these different situations. Okay, so what this wind farm suite can do is it can wake effects can be modeled for different wind directions. You can do a quantitative assessment of different layouts, wind directions, different turbine models, surface properties, and so on. Okay, and all of this is very, very cheap because these are very simple analytical formulas. So this takes only a few seconds or a few minutes to run. All right, and so we are constantly improving on this. We have a basic set, but we are adding more physics and incorporating more and more models in this as we go along. So that's it. So my last conclusion of my last point is CFD solvers will give you the full details, and it will give you rich information. It will give you a lot of data that you can use for developing simple models. And then those simple models are appropriate tools for doing design studies. All right. Okay, any questions before I wrap up? Yeah.
You have shown that there was a sequence of turbines, and with this
40? 43 you said, right?
Sorry,
Which one? This one?
actually it was a sequence of turbines with showing power generated by each turbine. There's a spike in the experimental one and not there in the theoretical one. So you said that the spike is because there was a gap between all the turbines. So if we can increase the power spike, so if we analyze the distance between the two turbines and we create the same distance within every, so will we get that amount of power spike for every turbine?
Yes, yes. So I think maybe you're referring to this one. Are you referring to this one? Yeah. Yeah, so this spike is because there is a larger gap here. So this turbine sees the wake of this turbine after it has recovered to a much greater extent. So yes, I mean, if you manage to keep this spacing between every 2 turbines, this level is at about 30%, it will move to maybe 50% here. Right? So all these numbers will move up if you increase the spacing here. That is true. But your challenge always is you have a finite amount of space. So given a finite amount of space, you want to pack as many turbines as you can optimally. So yeah.
Sir, we are talking about the vertical if the wind is horizontally, will this horizontal compaction also affect the turbines?
The wind is primarily horizontal. It's not vertical. What do you mean by vertical and horizontal?
Sir, because we are talking about distance that is taken from here, that between two distances. What if this horizontal, the compaction between two rows is
Hmm.
also affecting some?
Correct, correct. Correct, correct, yes. Correct, yes. So if you take this as x and this as y, then will this spacing also affect? Yes, it will affect. Typically, I mean, if you know that the wind is only going to be along one direction, then the spacing of about 3 diameters is enough. If you bring them closer than 3, then they will affect each other. If you bring them 3, 4, 5, won't make too much of a difference. But again, what happens is you don't have wind from one direction. You have wind changing constantly. So, yeah.
So these are all only these studies are for horizontal axis wind turbines.
Yes, these are all horizontal.
This can be extended to vertical axis.
Yeah, yeah. Vertical axis wind turbines also have a wake. Their wake is quite different from horizontal axis turbines. But yes, I mean, if you have a cluster of vertical axis wind turbines, their wakes will also interact with each other. Yeah.
So instead of having in this slide, if we stagger what with
Yeah, so staggering and all that is can be done. So I mean, if you just take this, and if you consider wind that is coming, say instead of 225, it is coming from vertically 180, this becomes a staggered configuration. So the purpose of studying this is because this is the worst case. This is the worst case. So given this layout, the worst direction is this. And so that's why you study the worst case, and the other directions are going to be anyway slightly better than this. All right, any questions? Okay, then let me wrap up. Yeah, so what I've shown you is that I've tried to give you a flavor of what are some considerations that are needed to do a wind turbine design and a wind farm design. And I'll leave you with a few tools that you can use if you are interested in pursuing this further. So this one is developed by National Renewable Energy Laboratory in the US. It's called SOFA. This is an unstructured finite volume C++ CFD code. The other one is one of our in-house codes, which is called PADEOps, and that's a structured finite difference Fortran-based code. It's also available on GitHub. And then we've developed this wind farm suite, which is the simple analytical models, which is also available on GitHub. And I hope I conveyed to you that this is a very interesting problem if you're interested in fluid mechanics or different aspects of mechanical engineering. And it is, I would like to believe it is of importance to our country's economic development. Okay. All right. So thanks a lot. I guess we'll have a tea break now, or I don't know if we have the next session right away. Thanks.
Hello? Yeah, now it is working.
Welcome back. So the next session is by Dr. Pradeep Mimula.
Yeah, thank
He'll
you.
be talking on smart grids. So let's invite sir for the talk.
Thank you, thank you. Let me just open my presentation. Okay, so good morning all. Today I am going to speak about two sessions actually, that is about smart grid, and also in the afternoon I am going to talk about the campus energy monitoring system. So smart grid, of course it is also a practical subject, but comparatively speaking the next session that will be after lunch, that will be more on a practical sense what we have done. I will be showing some case studies. But before that I will be showing like this. So here my mail ID is also there. You can, of course this mail ID is also changed now, just e.ith, but anyway I will share. So but before I jump into my presentation, I would like to just generally get the sense of the audience, what are their background. So for example, if I say how many of you are from electrical subject, electrical background, can you please raise your hand? So electrical engineering, or okay, electronics also. And what about the others? What all other branches? Mechanical. Okay. And what about physics? Chemistry. Okay. Okay. Oh, chemical engineering, and your materials. Okay. Oh, in that case, it will be good because this presentation is a general presentation suitable for all. So maybe you will get the benefit from this. So, and if you are interested to know more about this subject, maybe I will also show some of my other lecture videos which are available online. I will be showing. Okay, so with that, let me jump into the subject. And then not only this topic, related to these topics, I have so many other ready-made slides which I can jump into. So for example, we are discussing and suddenly we say, what about electric vehicles? Then immediately I can open electric vehicle and we can discuss something about that. So it is all like a, let's make it like a unstructured and like a free flow kind of discussion. So with that, let's go with this. So you are comfortable with the presentation here, right? You are able to see it properly. So, and my voice also is clear, I believe. So this is the general layout of power system. Okay, so if you see the general layout of power system, we can say G, T, D and C. Okay, G is generation, T is transmission, and D is distribution, and C is consumption. So for those who are from not from power systems or electrical background, so you can see this is a simple diagram which shows the supply chain, so called. So let's check this. So I think, so here if you see, we have generation. So at the top you can see coal plant, nuclear plant, hydroelectric plant. So these are in the scale of thousands or hundreds of megawatts. So large generation plants are there at the top, and this one is extra high voltage transmission. Then power comes down, and then at this level there is a high voltage transmission. Here we can have a medium sized power plants, maybe like 30 megawatt here, like at the industry level or factory level. And so on the left side, if you see, it is mainly two activities, that is generation of power and transmission of power. And actually the diagram is continuous, so I just made it into two halves. So here you can see the distribution starting now. So there is a distribution transformer which step down the voltage, and then here we can have a city level, or you can have a rural level and all. And here there will be again some industrial consumers and city level power plants and all. And at the bottom you can see solar and wind also coming into picture. In this diagram there is no electric vehicle, but you can see there will be electric vehicle also in this particular diagram because it's slightly older version diagram. So this is the structure of the power sector. That is not yet smart actually. Right now we cannot say it is still smart, because the power flow direction is from G to T, from T to D, and from D to C. So it is always a one-way direction of the power flow from the generations to the supply. But because of this addition of the solar and wind at the lower level, now there is a chance that the power flow direction can be reversed also. So we need to address that point also. So let's continue. So if you see, this is again what we call as a load curve. Okay, load curve means on x-axis we have load, that is the time on x-axis, and on the y-axis we have the amount of the load measured in megawatts in this case. So you can see this is actually, each one is 1 day, so it's about 6 days of data. So 1, 2, 3, 4, 5, 6 days. So during the day, what happens is at the beginning of the day, that means at midnight, the power demand will be less. Okay, so this is for the entire city of Delhi, for example. So the power consumption will be less during the midnight, and then slowly as morning starts, the electrical consumption or demand on the grid will increase, and then you can see there is a small dip in the afternoon. So that is the lunch break in the afternoon, and then in the evening again the power consumption will be more, because once the sun set, and then there will be everybody will be switching on lights and all. So this is a typical daily pattern. Okay. So what we call as a load curve we call. So we can make it for Hyderabad, we can make it for Delhi or different states, or even the entire country we can make a load curve. Now the question here we will ask is, this is the demand that we need to meet. Okay. So in order to meet this power demand, we need to have a generation to meet the demand. So what should be the generation capacity, okay, to meet the demand without any power cuts or anything? So then obviously we will see what is the maximum. So here you see maximum, and on the y-axis if you see, the value is around 3200 megawatts. Okay. So if this is my load curve, to meet this demand I need to plan a generation capacity of at least 3200, because in the evening peak I have to meet it. Okay. Now what is the breakup of this 3200? So 3200 can be coming from different technologies. So as I showed earlier, if you see, we have a thermal power plant or coal plant, then we have a nuclear plant and hydroelectric plant like that, and now if you see, there is a bulk solar, wind, all these renewable, geothermal, so many other different types of supply sides are also coming into picture. So in order to meet this peak demand, we need to plan the installed capacity, but there is immediately you can see one problem. Okay. What is the minimum during the night time? For example, if you see, this is like around 2000 only. Okay. So the minimum of your demand is 2000 megawatt, and the maximum is around 3200 megawatt. So almost it is like a 70% variation within 24 hours. Okay, huge variation is there. Now, but then you have to meet the peak demand, so you install all this, set up all these generation facilities, which are huge investment cost. But those generation facilities will be underutilized. Okay, so for example, if I say, if you see there is a continuously 24 hours there is some load, that part maybe we can say, okay, some nuclear or whatever thermal, whatever is meeting that. But wherever this variable part is there, you need to maintain the load generation balance and all these things. And in that process, certain generation units will be underutilized. So that is one big problem, how to address that. And similarly, if I go back to the earlier diagram also, there is another problem how to maintain the infrastructure, the electrical grid. Okay, without all these, so many components are there. You can see there are so many distribution transformers here, and there is a feeders are there going to different homes. So all these feeders should not be overloaded, distribution transformers should not be overloaded, and there will be natural calamities or disasters, and still we need to reliably operate this grid. So that is one problem. And the other problem is the maintaining the load generation balance and doing it in a economical way. So this is the problem of the power system operation. Okay. So let's continue. Now here one more photograph we are having. So there is a big office building. This is actual photograph, from one building from Delhi actually. So you can see a lot of air conditions here. So everywhere there is a air condition for different rooms. So this is on one side. Like that, the building 4 sides there will be different air condition systems. Okay. Now AC means there is a central AC and there is an individual AC. For example, this building, if you see, there is no AC units. You can see everything AC coming from one central AC. So the question I want to now ask here is whether central AC is better or having an individual AC like this. So here if you see, for this window one AC, next window one AC, next window one AC, each office there is one AC system, independent, separate, like that. This is better or having a central AC is better? What do you think? So usage, okay, answer is based on usage. So let us give that more information. Let's say this is a commercial building, some office building is there, and there are some regular activities going on like that. Or you can even consider it as like, let's say some software company is there or some IIT like this. So if it is like a commercial or industrial, then you are saying central is better. So what is the reason for that? Why the answer is correct. The central AC is always economical in this case. That is the reason why this building also we are using central AC. But what is the reason why it is central is better and individual is not better? Okay, space management. Okay. So economics of scale, that is also the correct answer. So economics of scale means, let's say even if I count now, so for example here itself there are 10 and 10 more here, again 10, or like if I just roughly estimate also, on one side itself I can find at least 60 to 70 ACs here, and if you take 4 sides it will cross more than 200. Now assume that each AC is 1 kilowatt also. That is also less now. Now we are getting more high capacity AC. Even if you assume 200 ACs of 1 kilowatt, so total AC demand will be 200 kilowatts. But if you have a central AC, do you need a 200 kilowatt central AC? We actually need it lesser, because that is what we are saying economical this thing, right? Why? Because the losses will be here, more losses will happen in each individual this thing. But if you do it or if I just take a analogy of a restaurant, okay, let's say this is an apartment building and we are talking about cooking of food, okay, whether 100 flats, 100 kitchens, okay, 100 gas stoves, 100 people cooking, 100 utensils, 100 spoons, all, and then 100 people purchase all these items, onions, tomatoes and all these things. Or if I have a common kitchen where there will be only one kitchen and maybe a small team of 4 or 5 people making food for the entire 100 people, like in a restaurant. And they purchase, all the ingredients in bulk and, all these things. Okay. So to cook food in 100 people food in one big utensil, it will consume lesser heat compared to heating 100 small utensils in 100 different this thing. Same thing also, for example, bus versus car. So in a bus, if 50 people can go in a bus, rather than that, if you have two people going in 25 cars will take more power compared to one bus for the same amount of transportation. But why this building having individual ACs? If we know that central AC is better, why the individual ACs? Huh? More power? No, just now we discussed that it will consume less power. See, if you cook for 100 kitchens cooking 100 dishes, it will. Yes, more power consumption it will have. So it is not good, right? So usage pattern and what you were saying? So whether a central AC will have that flexibility that I do in this office I want, next office I don't want, and again next office I want. If that controlling is available, then that is required, right? Then otherwise, if it is like rigid, nobody we switch on everywhere and switch off everywhere, then again it is not good. Anyway, so that individual control has to be added. Okay? So how do we?
Because like this is like chiller is at different place.
Huh.
So you need to tap the air conditioning properly. So I mean temperature lose. Efficiency also matters. I think.
Yes. So based on general like high level analysis, you say that this is less efficient if you use individual, and then but then the point you are saying the proper design has to be done, chiller plant, water, everything has to be, the set points and all that things has to be done properly. Anyway, so slowly why I am showing pictures and talking like this is that I want to bring before the hero comes there will be all some build up they have to do, right? So there is in the topic today, smart grid. Okay, grid you forget. First of all, smart. What do you mean by smart? Okay, intelligent, smart, like that. So slowly I want to bring that topic. I am giving all this background. So intelligent, smart means again you all know communication technology needs to be there, information processing. All these things is there. Using that IT communication algorithms and all these things, how we can operate it. Okay, slowly I'll try to connect. That is the reason why we call smart grid. Okay, so another thing you see in the picture down, you can see the cars are there. So on one side of the building, at least now you can see at least 20 to 30 cars are there. Okay, and these are all petrol cars or diesel cars. Now, but then if you take the picture maybe 10 years back, something like that. But now if you go and look at the parking, few percentage will be electric vehicles. But maybe after 5 years or more, so the component of electric vehicles will increase more. Okay. Now again, let's say what is the power rating of the electric vehicle charging? Anybody have any, like for example Nexon vehicle you see, or any other vehicle, what will be the power rating of the charging of that vehicle? So 55 kilowatt like that you are saying. So that is little higher, maybe that's like a total maximum kind of thing. So normally we see like for Tata Nexon and all, it will be like 6 kilowatt, 7 kilowatt for charging and all. Okay, and if there are 20 cars, okay, 20 into 6, so that itself is 120 kilowatts of power. And then the interesting thing is there is some topic called V to G. Okay, vehicle to grid. Normally G to V is the grid will give power to the vehicle, but sometimes V to G is also one technically possible. A vehicle can give power to the grid. Under what condition? Let's say there is a power cut in the building. Okay, power cut is there in the building, and some critical loads are there. Of course, ACs are all non-critical, so we'll ignore them. Just now we made a rough calculation, 200 into 200 kilowatts AC load we ignore. But at least there will be some critical loads inside, maybe some important things. Let's say we require suddenly 100 kilowatts of power to operate the critical loads in that building. What is the source if there is no power, if there is a power cut and no grid? What is the source for that critical demand? We get that power from generator. There will be diesel generator, it will be generating power and switch on the generator. We also expect that. So if sometime there is a power cut, we expect that generator will be on. And the generator is giving that 100 kilowatt of power. Or another thing, there will be inverter and then there will be battery for a smaller homes. So now the thing is, these vehicles, if they are there and they are electrically connected to the building, why not use the vehicles itself to supply to the building, or the what I called V2G. So that also we can use as a backup. So in future that is going to also come up as a resource, because if you need emergency power for the building, the vehicles can help. So that yes, provided yes. So electric vehicles needs to be there, and because the battery capacity of the vehicle itself is also now high. Now 30 units, 40 units will store in the battery, and then if you pool 20 cars, so 30 into 20 is 120 or 600 units of energy are available. It is there, and maybe you can compensate later once you get the thing. So instead of investing in a battery storage for the entire building, this kind of thing can be used. So there are a lot of technical ideas are technically possible, but we need to work out the economics, we need to work out the policy and all. And of course we need to, when I say technically possible, we need to have the proper the layers, connectivity and some algorithms, some analysis and all that. Okay, so now if I go further, you see there is this city, right? So this one is the entire city. The city will have hundreds of buildings, and each building can be like this. If you see even Hyderabad or Delhi and all, so we can ask the question: can the building help the city, and can the city help the building? So what is the meaning of this? First one is building helping the city. So let's say at the city level there is a more power demand is there at the city level, maybe during this evening peak. So instead of investing in a centralized generator, okay, so somewhere some thermal plant or diesel plant or something like that, instead of investing crores and setting up a generator for operating in the afternoon, evening 2-hour duration, I can have a concept called demand response, and will ask the demand only to respond. That means all the non-essential loads during that period can be switched off or can be controlled. So for example, like let's say water pumping or washing machines. So these things need not be operated in the evening peak, because water pumping can be done in the midnight, or washing also can be done later. So basically what we are saying is that the demand should respond to the conditions of the grid, rather than the grid is being overloaded at a particular hour. So everybody wants to you switch on all the lights, then you charge your vehicle, then you wash your clothes, everything you want to do at 6 p.m. or 7 p.m. And that time the entire grid will become overloaded and more stressed. So that can be avoided by properly doing this. So that is what, so if there is a message from the distribution company saying that we need 500 kilowatts of demand response at this time, then anybody who responds to that message and provides that reduction, then they can be compensated. So this kind of thing. Similarly, city also can help the building. So if there are multiple buildings and one of the building requires excess power, it can be routed from other buildings. So like that. That is, we are again calling peer-to-peer energy trading kind of thing. Okay. So let's say there is a big industry and behind that there is some unused land. So whether somebody can set up a solar plant there and sell power to that building. So it need not be that only the distribution company should generate power and sell. Anybody, third party, can sell power to each other. So such kind of thing also. Now I will change the topic further again, because that's why I said the audience are different specialization. This will be a general subject, so everybody can follow. So what I am calling it as a retail grid. Okay? So right now there is no retail grid, but it is the vision. So in scenario 1, you might have seen like this. It's a small shopping complex with 10 shops are there, and then there is a distribution transformer selling power to all these shops. And this red color box is the energy meter. Okay. So now this is scenario 1. So what happens here is, if there is an interruption in the incoming supply, distribution transformer interruption is there, then what happens? All the shopping complex, all the shops will lose the power. There is no power supply. So as you know, if it is a shopping and if lights are not there, then the customers will not buy, nobody will buy anything. So what do shops people have to do? They need to plan for a backup supply. So whenever they are setting up a shop, opening a shop, whether they have a backup or not. So that is our scenario 2. Now I will go to scenario 2. So in scenario 2, what is happening is each shop will have their own, in the corner you might have seen again, small DG set with a inverter, battery, something like that. In one corner of the shop they keep that generator. Whenever there is a power cut, they immediately switch on that, and then the lights will come back. In fact, the customers also expect that. Customers will expect that if the light is gone, they will still sit. Maybe they will check their phone sometime, but within 2-3 minutes they expect that light will be on, even if there is no power from the distribution company, because generator will be on. But the question is whether this is efficient, whether this is the best way to address it. So again, the same logic what we discussed earlier. 10 shops purchasing 10 diesel generators, 10 people purchasing diesel, filling it and then operating it and all is little inefficient. Okay. So what we need is the option 3, that is scenario 3. So it is something like this. There is a one, for this entire shopping complex, there is a one common generator, and they are generating power, and then they are supplying to all the shops. Now the wiring is different, so there is a changeover switch kind of thing. Right now my switch is towards a grid. I am getting power from the grid. Now when the generator is on, I will just simply change over the switch, and now I am getting power from the diesel generator. Again, this will be cheaper, because what happens, sorry, I went to, yeah. So this is scenario 3. So here each shop will have two different meters. One meter for the main supply, and another meter is for the local diesel generator. Okay. So now I need to pay the 2 bills. Okay. But this is still cheaper, because if I go back to here the diesel bill will be more compared to how much it will be, because this is little more efficient to operate. So, but the question is now, here one interesting question comes into picture. Let's say this is actual shopping complex, and from here we are getting supply from the local distribution company. Like for example, here we have TS SPDCL, Telangana South Power Distribution Limited, something like that. Meanwhile, some third party fellow, private fellow, sets up a generator, sets up the wiring, and sets up the metering, and collects the metering bill. So question is this legal or illegal? So what I am showing on the screen, is it a legal or illegal? Yeah. Huh? Illegal. Okay, so see, I mean some places, but then actually if they do also, it's not possible to track also, because it can all be there, it's all distributed. Yeah, so sometimes strictly speaking it may not be legal. Okay, but it's a better solution. See, this one is a worse solution, but this is, maybe you can say it is legal, but then this one is a better solution but illegal. Okay, let's continue. I mean whether it is legal or not, we'll continue our technology development and we'll see later. So now scenario 3. Scenario 4, you see, compare 3 and 4. Okay. In scenario 4, what is happening? Instead of a separate wiring and separate metering, I want to have a common meter. Okay, so one main meter will measure the total generation, and then I want each shop will have like this. Okay. So, but what is how will we able to identify here? How will we be able to manage the bills? So can you see what is the problem? Like here there is no problem, 2 separate are there, but here it is common. So what will happen in this case? What is the additional step we need to do in this case? Hmm? Okay. Okay, so that's a answer in a correct direction. We need to be able to distinguish that. See, normally what happens, if you see your current bill, in the bill they will say this month total units consumed. So let's say 172 units consumed. Like that, some total number of units consumed in the entire month, you will get that number total. Here I want to distinguish between maybe let's say 70 units coming from diesel generator, 100 units coming from the, I want to be able to distinguish that. Okay? How we will be able to distinguish? See, if it is a 1 meter and then making a continuous counting for the entire 1 month, then it is not possible. We need to have what is called as a smart meter. Now we are entering into smart. So what is a smart meter? The regular meter, what we have, the regular meter you will get one reading in 1 month, because the meter reading person will come and you look at your meter, previous reading, present reading, you will subtract and then say this month this is your bill. You will get the current bill if you have seen your current bill. That is the process right now. So with the smart meter, what happens, instead of one reading in 1 month, we will get one reading every 5 minutes or every 10 minutes or 15 minutes. We can get continuous reading. Okay? Obviously, because there will be crores of meters like this, it cannot be manual, it has to be automated only. So that is why we call AMR, automated metering reading, and AMI, automated metering infrastructure. Okay, so these things are there. So if you are able to collect the energy consumption pattern every 5 minutes, every 10 minutes like that, and then I know at what time this one is switched on and at what time this one is switched on, based on the timing of this thing, as he was saying, logical switch. So basically logical means software. So in the software I can distinguish, saying that the software will calculate, even though one meter is giving data, the software will calculate this many units coming from outside and this many units coming from here, and this is your bill. And the rates also can be different. This may be slightly different cost and this may be slightly different cost, and then that is all okay based on the requirement. So here is where you now look at the requirement of the data. So if you get one reading in 1 month compared to one reading every 5 minutes, for example. If 5 minutes means in 1 hour 12 readings. In 1 day, I think 12 into 24, it will be coming around 144 or something like that readings. 288 readings will come in 1 day. Okay, round off to 300 readings in 1 day. So in 1 month, so 300 into 30. So it will become 9,000. Okay. Earlier you used to have one data point, now you are having 9,000 data points. So earlier you had maybe one small computer, or maybe 5 or 10 computers in that electricity department will have some billing software, something like that, right? Earlier 4 or 5 computers may be sufficient, but now the amount of data increased by 9,000 times. Okay, so you need to have now major data centers to process all this data. Now you can say, why we need to do all that, why not continue our old system? Yes, you can continue, but then the technology is developing, these generators are available, meters are available, and everybody wants to go to the best solution technically. So you have to, now all the power companies have to invest in so much of IT, software, data, all these things. Okay? So, yeah. Scenario 4, right? Now scenario 5. So in the scenario 5, if you compare 4 and 5, now again there is a solar panel, there is a battery, there is a wind, again one more solar panel, again some electric vehicle. So all this renewable energy is getting integrated even at the retail level. So it's not a wholesale level, it's a retail grid. That is why the title is retail grid. So now what happens, let's say shop number 2 is having a batteries. Okay, so there is no other business. The entire shop itself, they set up batteries. Okay, and all these batteries the entire room is filled with batteries. And what they do, whenever the demand is less in the rest of the grid, they will charge. And whenever demand is high, they will sell. So basically they are buying power and selling power, the battery, charging and discharging. In the process, they will be able to make some profit because the rates may be different. Okay, so that is time of the day tariff and all. So such kind of things going to come. Also there can be, see here we see how many buyers are there, okay, how many people are buying power or how many consumers are there. So for example, you say, okay, 10 shops are there, there are 10 consumers. But the number of consumers may not be 10, okay, and number of producers here, see there is one local generator here and one supply here, only 2 producers. No, there are multiple producers also. So the number of producers also increasing, number of consumers also increasing. So consumer plus producer. Do you know what is the term? Producer plus consumer. Prosumer. Okay, there is a term called prosumer. They will produce and they will consume also. Okay, so who is this prosumer? So prosumer is the one who can. So now the thing is, nowadays, see so the entire world is going to prosumer concept. Okay, earlier newspaper you used to get. Who is going to make the news? So only some big building will be there. They will have journalists. They will go to the different events and they will take photos and they will collect the news. And then they will, in the night time, they will prepare the newspaper, midnight sometime like that, and then they will go for printing, and next day morning they will give. Okay. And we have to wait for the newspaper to know what happened in the city. Okay. But now what is happening? Everybody is a journalist. See, if I want to become journalist, what I will do, I can always go to some event. Okay, today we are attending ANRF energy, workshop in IIT Hyderabad. Then you take photos, selfies, and all, and you keep in your LinkedIn, you keep in your YouTube, or you can keep in. So you are all, see, nobody has to wait for a newspaper to come. So you are consuming, and we are also consuming. Whereas your colleagues may be attending another workshop in some another venue. So like that. So people, everybody is now producing information and also consuming information. So in the information terms, we are all prosumers. Okay? But what about energy? Okay? We are all consuming energy, but are we producing energy? So we also have to produce energy. So no longer we'll say we purchase land, we purchase gold. Now you invest in solar panels, generate some energy, let it put 1 meter, connect to the grid. Every month it will keep generating some energy and you will get revenue. So instead of, that is also one type of investment now. Okay, so people can start investing in energy, because we have a big target, right? 5,000 gigawatt is a government target, and in that significant target has to come from a rooftop. And you are having rooftop. So I don't know, like people living in apartment, there's a story is different. But if you are having a own house, if you are having a free roof, now the economics also working out. If you actually count, there are hundreds of solar companies also. They will give, and government subsidies are also there. So you have to make an initial investment, and then maybe payback period will be 2-3 years. After that, in the solar panel, if you maintain properly, it will work 10 years, 15 years, even 20 years. And your own bill will be zero. Further, you can sell power to your neighbor. Okay, so this kind of thing can happen. So just like how you are taking photos and posting on social media, you can also generate power and put the power on power grid. Okay, so now imagine, I'll just go back. Okay, so this diagram will change completely. So here we have distribution and consumption, and again after consumption there will be local production, distributed production, and then the power flow will become bidirectional. Okay, so like that. So just to see what are the drivers for smart grid. One is utilities require loss reduction, peak load management, asset management, renewable integration, and a self-healing grid. So these are all some technical problems. How to reduce the losses, how to manage the peak demand, okay, and how to manage all your assets, how to integrate renewable energy and self-healing grid. And the customer wants access to power, reliability, quality power, prosumer enablement, and choice of power purchase. And the government wants satisfied customer, reduction in emission. Utilities should be financially sound and tariff neutral system. So these are not all the full list, but some points we mentioned here. So to achieve all these things, we need a smart grid. Okay, so like that. So that was part 1. Okay, so see, part 1 is why we need smart grid. Okay, but what is smart grid, we did not cover. Okay, so normally, what is the ordering of the presentation? First we cover what is smart grid, okay, definition of smart grid and all. After that we will say why we need smart grid. But now I thought, nowadays in movies also they will show, directly they will show starting of the movie, they will show somebody admitted in hospital. Okay, then they will say, 1 month back what happened. Then they will go into, so like that. See, I wanted, so that's why it's all pictures and diagrams and all, to show that, see, you get the thing that, okay, the situation becoming complicated. Okay, it is not straightforward, it is not like a regular power grid. The situation is becoming complicated. How to address this situation? So first that part is that one. Now what is smart grid? Briefly I will enter into that points. Okay, so and afterwards I will also break. I want to get some questions from your side. Okay, so what is smart grid? So you can think of this smart grid as a layering of infrastructure. So there is a physical layer, there is a communication layer, and there is a information processing layer. 3 layers are there, and this can be also smart X. So where X can be smart grid or smart traffic, smart water, smart anything, like so many other things also you can relate this depending on your this thing. So in the physical layer we have physical infrastructure. So in the case of electrical system, what we have, in the case of electrical system, these are all physical components. So maybe you have transformers, you have capacitor banks, you have power lines, you have solar panels, inverters. So all these electrical hardware systems you are having. Now, in order to that all this electrical hardware is functioning properly, that there is no overloading, there is no failure, nothing like that. All the things, in order to have that, we need some kind of a communication. So right now people, I see 2 people with phones. So whenever there is any problem here, let's say some machine got breakdown, some transformer not working, then somebody will give complaint saying that the transformer not there. Then that complaint message will go through communication and go to the information processing layer. Again, there are a couple of people sitting here at the top, they will register the complaint, then they will try to send the repair people and all. Okay. In fact, the same case is also, let's say in your house, you may be having geyser, you may be having washing machine, water filter, oven, etc. All these devices are there. If let's say there is a washing machine, there is a problem. So what happens if the washing machine not working properly? Then you have to find out the customer care number, then you have to call, then they will say press 1 for English, press 2 for Telugu, all these things. Then you have to wait, then they will say when did you purchase? First of all, you are the real owner or not, what is your address, what is your date of birth, all that things they will ask. Finally they will send, our technician will come. Here we have human being in the operation. So here see, a person is making a phone call. Okay. Instead of person making a phone call, let's say they develop intelligent smart washing machine. Okay, smart washing machine, what it will do? It will check what is the problem, whether that problem can be solved locally or not. Maybe some filter needs to be cleaning, whatever like that, or whether some inside some component is burnt. Maybe the main motor winding got burnt. Then obviously the resident cannot replace the motor. So depending, the smart washing machine should sense what is the problem. Sensing what is the problem, it should only make the call. Okay, because nowadays washing machine also connected to Wi-Fi. So through Wi-Fi it can send a complaint, and then the person should recognize, okay, this part is missing, something like that. Okay. So again, just to, since I am discussing, we can even make it in such a way that the washing machine company, whatever LG or whatever washing machine company, they can send a drone to your house instead of sending a person. Okay, the drone will have a small box, inside that the component will be there. Okay, so it will fly, and you kept your, where did you keep your washing machine? You kept it in the balcony. So no need to come to your main door also. So the drone will come from the balcony, land in front of your washing machine, then the drone will convert to robot. Okay, the wings will be folded, and now the hands will come out. Then it will open your washing machine, and then from the stomach it will replace the component. Then again it will close it, and then it will fly away, and your repair is done. Okay, and the payment also will go automatically, because you might have already, online payment anyway we are having already. We don't have that part anyway, we are already having. Other part we need to do that. Okay. So that is where we are saying layering of infrastructure. how efficiently you are sending the information. Okay? So I have just given one example. Why only for repairs? Even for ordering also. So let's say I'll give the fridge will scan the inside the fridge what all things are there. So if I give a condition that all the time there should be maybe 1 liter of milk should be there. So you take the milk and use it, then immediately it will scan that okay it is gone. Then again fridge will place order, then the drone will come and it will deliver to your fridge. Okay. So the more you remove the human beings from the loop, then it will become smart and it will become, because unnecessary time waste, right? Making the phone call or going to shop, putting the order and all that. Anyway, so now this here you see at the top I am saying not smart. Why not smart is there in the title is because there is a human intervention in between. Okay. Also if you see here I have kept a horse also. Why horse is there? So in olden days mode of communication, horse was also one mode of communication. Okay. So like the king is sitting at the top, information processing. Then if the enemy army is coming, then immediately they will check, and then on horse they will run, and then suddenly they will come and announce that enemies are coming. Now what if there is WhatsApp, okay, at the time when the kings were ruling and all, at the time if WhatsApp is there, that fellow can take a photo and then send it, then the king will get the immediate message, okay, this much army is coming. So like that. So the information processing can make it more smart. Okay. So that is what is this one. We call it layering of infrastructure. We need all the physical assets to be sensorized. So this star mark is what? This is a sensor. Okay. So this star mark is a sensor. So temperature monitoring, pressure monitoring, whatever, current monitoring, power monitoring, whatever parameters. So any asset you have sensors, they will be continuously monitoring. And what the sensors will do? Sensors will send they are connected to the information layer and they will send the data to this one. At the top there can be servers, there can be automatedly, like there may be a system only processing them, or there can be a human being there who can just also process. So by doing this we are able to make it smart. Okay. So now we can call this as smart because we are collecting continuous information, regular information. Here human intervention also not required. So that way. So now comes the question, which layer is the biggest contributor of smartness? Okay. So whether it is becoming smart because of the physical layer, or becoming smart because of the communication layer, or becoming smart because of the information processing layer. So which layer is the biggest contribution? All of them are contributing, but which layer is the biggest contribution? So the information processing, okay, we already have one. Anybody want to say communication layer? So let us analyze this further. So how system will become smart? Okay. So there is this layering of infrastructure, physical communication information can be taken analogy with our human body also. So the muscles are equivalent to physical layer, nervous system is equivalent to communication layer. If you talk within the body, so earlier it is a infrastructure, the power grid or something. Now within the same body, the brain is equivalent to information processing layer. Okay. So megawatts flows in the this one, and communication is megahertz, and information is megabytes. Okay. Now the thing is, since we are discussing about analogy with human body and all, we can compare human being with other animals. Okay, let's say you compare human being with a lion or a tiger, or compare human being with a monkey, or chimpanzee, like that. Okay, so if you see the muscles, okay, so the human muscles compared to lion, tiger, or chimpanzee, like that, we are actually weaker. Okay, so we cannot jump that much, or we cannot run that much faster and all. What about nervous system? Nervous system means your reflexes. Okay, so how fast can you? What is your reflection? So if you see the racing cars, the drivers driving the racing car, within few milliseconds they have to take left turn, right turn, and all these things. Because you have to look at the scenario, understand the traffic condition, your brain should give command, then you have to take the driving and all that. So in that also, if you see, some of the animals are much faster. So like, so human beings are comparatively less in the physical layer, less in the communication layer also. What about information processing layer? So that is where human beings are better compared to other animals. Okay, how we are better? So we have language, we have mathematics, we have some kind of symbols, some kind of communication system. So because of all these things, we are able to live better and be safer compared to the other animals. So that's why we say human beings are intelligent. So why is? Because of our top layer, information processing layer. Okay. So the more information processing layer is better, the more we can make it. Okay. So see, again you might have seen phone and a smartphone. So everybody now uses smartphone. So what is a smartphone? So smartphone means it will again have these three layers again. There is a physical, then there is a communication, and there is a information processing. So let's say now I'll ask one interesting question. Okay, there are 4 people. All 4 people are using, let's say, latest iPhone 17. Everybody having iPhone 17. Okay, and same network provider, either BSNL or Airtel or whatever is the signal is same for all 4. Now all 4 are equally smart, or one phone is better smartphone and other phone is less smartphone? Huh? So all phone iPhones are equally smart. Actually, anybody want to say that no, iPhone number 2 is more smart compared to iPhone number 4, like that? See, the hardware is same, purchased, manufactured same date, same shop we purchased, everything is same. Except that the information processing part, can it be different? Huh? Huh. So it depends on the usage of the person who is using the phone. So 4 people are having iPhone. Now it depends on what apps you install. Okay, so everybody goes to App Store. Somebody will install games. Somebody will install some productivity tools. Somebody will install some AI chatting and all that things. So depends on what kind of apps you have installed. And see, the sensors and communication, everything is same. But depending on what kind of apps you are installing, one person will be wasting time, whereas the other person will be maybe doing some coding in the background, or some reported automated emails are going, something like that. So it all depends on, every phone is smart, but some phones are more smart because of the applications that are running inside that phone. Okay, you agree with my analysis, right? So some phones will be smart because what apps you are using. Okay, what contact list you are having. So you have all friends who keep on disturbing, then your time is gone and all like that. So how to become a smart means your phone you need to use properly. What kind of unnecessary apps you need to delete and all like that. Okay. Now come the same thing. There are, like, let's say I usually tell to my students, because now here some of you are also teachers. So usually students are there. 4 students are there. Okay, who is more smart, who is less smart? How do you decide? So it all depends on. We will not say, okay, 4 people now fight. Then who is the winner in the fight? They are smart. No, right? So the physical layer communication, we give more information, more stress on the what kind of apps are running in your head rather than the phone. So what is your thought process? What is your thinking? So although the lecture is about smart grid, I am also saying smart student, smart human being. In terms of what are your thinking? What are your thoughts? So try to make that thing. So you can become more smart. Going back in this diagram, so let's say we are talking about power grid. Okay, the power network, power system thing. Question is it smart or not? The answer is how much is what percentage of your electrical infrastructure is metered, and sensors are there, and you are collecting the data. But just keeping the sensors and collecting the data and having a data center and having gigabytes of data and not doing any analysis again it is not smart, it is dumb only. So collecting the data is the big challenge, but even bigger challenge is once you collect the data, you have to process that, you have to get some insights from that. And the same thing goes in all domains. So let's say smart water system or smart transportation or smart health system or smart finance, all these things, you need to have some whatever apps which are processing the information properly. Okay, so that way. So that is what is the thing. So finally, this is the definition of smart grid. So the definition available in Wikipedia. So so far last I think about 40 minutes, 45 minutes we are discussing. All the discussion covered in this one slide only. It's very interesting definition, you can see. A smart grid is an electrical grid that uses information communication technology to gather and act, okay, on information about component systems, suppliers, consumers in automated fashion to improve efficiency, reliability, economics and sustainability of the production and distribution of the electricity. So this is like a standard definition for what is a smart grid. Okay. So here there is act also, not only gathering. Okay, so there is acting on the information. So unless you gather the information and take a decision and you act on it, that is the thing. So yeah. So briefly, I will stop here. And any questions, anything you want to ask until now? Yeah. Any doubts or any? Maybe you can relate to your background, your research topic, whether. It need not be specifically on smart grid also. Generally in the line of our discussion, you want to ask anything. Any
plug-and-play systems which can make a normal grid to a smart grid?
Okay, so the question is, are there any plug and play system which can make a normal system into smart grid? We can answer that in a few ways. So maybe by giving some examples. So right now, as per this, we need to collect the information and we need to act. So there are some like a smart water pump, for example. So I think if you search online also, you will find that product also. So what they do is your water tank is on the rooftop. You are pumping the water, and it will sense the level, and if the level is reaching, automatically it will switch off. Otherwise the water will be going down. In the earlier days, I think even from my own childhood I can remember, so usually it is a job of the kids to check the water level. Then they have to run up to the top and then see, okay, more 5 minutes, more 10 minutes. So I used to say this much, this much, this much. Then based on that, parents will get idea, okay, then we have to switch off. So now that can be automated. So that is one example, plug and play. That is at the smaller level. So like that, yeah. Yeah. So any other questions on this? Okay, so what I suggest is still there are some more information. I'll just go forward and then maybe we'll conclude in maybe 5 to 10 minutes. I think around 1 o'clock is your lunch break, right? So last 5 to 10 minutes I'll conclude, and then there is one more session later after lunch. I think the venue also different. So I don't know why they are not continuing in the same venue. There is a seminar hall in electrical department. So I think maybe the organizers will guide you. Anyway, let's quickly see. See here, smart grid is an interdisciplinary area. So we need power engineering, the regular power system studies. We also need information technology. We need communication technology. We need regulations and policy. We need economics. We need social sciences also. And finally, all of this comes into smart grid. Okay? In fact, only the top one can be changed. So let's say we are talking about something related to smart transportation system. So then here at the top, instead of power engineering, there will be transport engineering. Okay, and then information, communication, these all is common. And then finally in between it will become smart transport. So like that. So you have to relate it to different domains. So no longer now, because now the problem is all the subject what people are learning. Okay, they are going into civil engineering, they are going into mechanical engineering or whatever engineering they are going, and they are sticking to that only, that is this top one. But everybody, common subject, everybody has to learn economics. Okay, everybody has to learn about communication technology, how the communication work, how Wi-Fi works or how network works, information technology, how to handle the data, how to create a database. So all that things. So that is why what we say, let's say we are teaching about, let's say motors. So we should not teach the working principle of the motor only. Motor parts, working principle, and then some numerical problems. No. If at all I want to make this motor into, I want to store the motor data in a computer, what should be the structure of the database? What should be the columns? What should be the rows? You know, and if at all this motor having any problem, how to identify? So let's say I am getting a motor operation data of last 6 months. Looking at the data, can you tell whether the motor is working efficiently or not? Whether any so this kind of questions are not there in the subject now. So normally what we teach is, okay, motor means it will have one stator coil, one rotor coil, electromagnetic induction will be there and working principle, and it will work. So we are only teaching the working principle, construction, anything. The same can be even mechanical, civil, any other subject also. Let's say dam is there. So what is the working principle of a dam, our height and all these things we'll say. Then to attach to that, there should be some information technology, communication, something like that, or some bridge is there. So I want to construct a bridge. So then we have a database of 100 bridges. So out of 100 bridges, which bridge is better, which bridge is well designed, they should be able to again process the information and that kind of thing. Again, if you remember the 3 layers what we said, the top layer is the information processing layer. So whether you are able to write your domain specific problems into form of a analysis, like that. So I'll go little bit into just to show how further it can be drilled down. Earlier I showed GTD. G is generation, T is transmission, D is the distribution, and C is the consumer. So these below 4 are the traditional domains. Additional to these traditional domains, 3 main domains are coming. One is called markets, other is called operations, and other is called services. Okay. So this is called NIST, that is National Institute of Science and Technology. This is based in America, USA. They have developed this conceptual model. This is like a similar to one map, like we have an India map. So different states are there, like that different things are there. Now the earlier people used to be transmission engineer, distribution engineer, or a bulk generation technology engineer, like that. Now we need services, operations and markets also. So there are people who are working in power markets. So who requires power, how much, selling bid, buying bid, market, all that things. There is a power market is again a different subject. Okay, so, and operations means there will be a control center, from there you will operate, like that. I'll quickly go through further details. See, if you go to this generation, I'll skip this. See, in the generation, there are again different classifications. So here you have non-renewable, non-variable, that means the traditional nuclear, coal and gas. Then we have renewable and non-variable, that is hydro, biomass, geothermal and pump storage. So these technologies are renewable energies only, and they are non-variable. That means you can control them. You can increase the power output, you can reduce the power output. So all these things, biomass, hydro. So this is controllable and renewable. Whereas this one is renewable and variable. So here you have wind and solar. Okay. So what are the activities? Control, measure, protect and record. So these all activities are there, and all these powers will go into the transmission. Here we have transmission. So all the powers are going into the transmission side. Okay. So this is one example. Now in the distribution, what they are doing is they are distributing the power. So on one hand, the power comes from the transmission system. On the other hand, power goes to the end consumer. In between, there are sectionalizing switches, distributed generation, storage, and all these things are there. Here we have to control, measure, protect, record, and optimize. So these are some of the activities inside the distribution. And now the customer domain also exploding like anything. So there is classified as a building customer, industrial customer, and a home customer. And we can see there is a separate, like a multi-dwelling or apartment also is shown as one separate category. There is an electric vehicle also there. So these are all coming into the consumption domain. And everywhere the blue line is information exchange and the dotted line is the power exchange. So both information and power are being exchanged at all the places. So this is again like for example in industrial automation is there, or like a building automation is there. So these are all like now everything wants to become automated. These are all now very much required. Even appliance level automation, as I mentioned some time back. And everywhere there is a meter. So there is an energy meter here, there is an energy meter here, there is an energy meter. So everywhere you are doing metering. And everybody also plays a role. There is a service provider, there is a operations, there is a distribution, markets. All of this also providing this thing. So I was telling markets, right? So in the markets, what they do is market operations, market management, DER aggregation. Okay, so again, this aggregation is one of the main term. So what you are aggregating? So you might have heard about all these aggregation apps. So what are the aggregation apps? So for example, you have Swiggy, Zomato, Ola, Uber. These are all aggregation apps. So what they are aggregating? They are aggregating the consumers and producers. Okay. So same way there will be aggregation in the energy sector also, in the power sector also. So there will be aggregation services for, so in fact one example I can give, let's say now we can see a lot of general stores you can see where you purchase your regular, regular items like, oil and, atta, rice, biscuits, everything you purchase, right? Now the thing is they can always keep one, see there is a shop is there, on the other side of the shop there is a place to keep one vehicle. So they can attach one charging point there and somebody can park their vehicle, connect to that, and they will pay to that shop that okay I am connecting my vehicle here, I am charging my vehicle. So effectively what is happening? Along with selling the regular chocolates, biscuits, everything, that particular store is also selling power for the electric vehicles. Okay, because now there is a charging infrastructure is required. So now if that is there, so there is going to be like simply like you go purchase a milk packet, like that you go and purchase your electricity for your vehicle. So there are going to be thousands of sellers like that. Every shop will keep one connection point. It is going to happen in future. Okay. Now the thing is, now I am traveling from here to there. So now I want to check where I can charge my vehicle. So then we need a aggregation app. So I go to that like Ola, Uber, everything like that. Now I want to go from here to there. So I want to charge my vehicle. So from here after 50 kilometers in that region, is there any charging slots available? Then they will say some Pawan Kirana general store, one charging station is there. So this is the power capacity, this is the rate. Next some Bhavani, some shop is there, there you can collect. So like that you are going to get the, in fact one of my MTech student is doing a project like that, peer-to-peer selling of power for the electric vehicle charging, because in future so instead of going to petrol bunk and getting petrol, I want to have multiple slots where I can just simply go, and then I can, if it is a food court kind of thing, then I can charge and then I can have food and then vehicle can be charged. So like that. So that all things comes in the market. Okay. So operations. So again, as I mentioned, the drone will come and repair. So that kind of thing can come. Of course, in this diagram, they did not show drones. This is slightly older slide. And services. So this is like one more like a conceptual model to explain. Anyway, I think in the interest of time, I will stop here. Maybe one last round of questions, one or two questions anybody have, we can address that.
So can you tell some Government of AP is changing all the meters to smart meters.
Yes. So smart meter again is a earlier the meter only used to measure the energy, but how many units consumed during the 1 month. But now in the smart meter will measure the individual parameters also, like what is the power at this time, so that I should be able to get the power curve from morning till evening. What is my power and all like that. So load curve and all, and then based on that we can plan. Okay, so I think in the after lunch we are going to cover that. I have some examples, demos where we are using energy monitoring within a campus. So I can show that in the afternoon. Yeah, but yeah, smart meter. But then smart meter is only one component. And again, as I said, you install the meter, you collect the data, and the data is there in your server. But if you don't act on it, then again it is waste. So it's a waste of all that investment. So you need to take. So what all can be done using that? We can see. Yeah. So now, if somebody, I hope you will be able to explain. If somebody asks you what is smart grid, you should be able to at least engage 5 to 10 minutes. You will be able to speak. So yeah. And I was telling, right, we need to be prosumers, not only consumers of information, producers of information also, right? So if you are, how many of you are having your own YouTube channel? How many of you are keeping your lectures online? So it has to be done, because in the same spirit, like whatever you are doing, you just explain. See, for example, if you see, this is my YouTube channel. So you can see these are all the lectures on smart grids only. So whatever I told today, yeah, this one. So whatever I told today is actually this one. So it is already there on YouTube. I could have simply played it and then, see, you can see the architectural overview. And these are all like almost 15 to 16 hours of lectures are there on smart grid. So it is available. You simply search online my name, Pradeep Yamula, and smart grid, like that you search, you will find. This is smart grid 1 course. This is smart grid another course, more on like a appliance monitoring. This is some lectures on renewable energy, and this is some industry lectures that we conducted in IIT. So you can see. Okay, so these all things are available. Yeah. Okay, so with this I will stop here. Yeah. So yeah, thank you.
So now let's thank Dr.